Okay, so can you hear me?
Yes.
Okay, good morning, everyone, and
Yes.
thank you for joining this workshop in your busy time. So I want to welcome you to the Shibaura IT virtual workshop on materials for energy. Okay, let me introduce in detail the scope of this workshop. So we have several grand challenges to solve. This slide is borrowed from Professor Gang Chen, MIT. And these challenges are climate change involving CO2 emission increase and global warming, population growth and energy demand, and also the water scarcity in some region of our planet. As a scientist involved in material science, we are called to give our contribution to solve these issues in a sustainable way. Sustainability can be defined in many ways. One is this here. We have to consider not only the needs of ourselves in the present, but also the needs of future generations. And in a schematic way, we can represent sustainability in this graph, considering three main aspects: is environment, economy, and society. So sustainable development is the intersection of environment, economy, and society, and can be quantified by this formula, which is called the Kaya identity, and contains all the aspects of the challenges I show you at the beginning. So carbon emission, carbon CO2, CO2 emission, global world population, economy, and consumption. So you can refer to the literature for details. And the result of this calculation is this kind of graph reported versus year. So we can see what we know more or less already. So increasing of CO2 emission, increasing of population, and how the economy is going on. And this is for the world, but we can calculate F for each nation and region. So each nation and region has different trends. And this is about CO2 emission in particular. So the black curve is actual emission, and all the other curves are extrapolations following different models. So especially the red one, and is what happens if we do nothing. And the other models are what happens if we act in a sustainable way and do our part to reduce emissions. So there's no time for details, but it's clear that the situation is not easy, not good, and we have to do something soon. So how to sustainably develop energy resources, which means how to decrease F, how to make F small. So just looking to the formula, we can minimize P, which is of course not easy, not just science, but is related to political and social issues. So this we cannot discuss this in this workshop, but it's a big problem. Make G small means reverse of economical growth or recession, so which is not sustainable. We have to reduce E or F, small f, which means reduction of demand and or reduction of energy supply. Substitution of energy supply with something alternative, which means use of renewable energy sources and introduction of materials, advanced material in energy landscape. Energy landscape is this one. It's the global vision how energy is supplied, carried, stored, transported, and finally used. So we can find in this diagram all the possible energy sources, renewable and non-renewable, and how they are transported and used. So the point is how advanced materials can be inserted in this landscape, and how can help us to solve the global challenges. Here you can see advanced materials can be introduced and can be their part in all of the steps of energy landscape. So the scope of this workshop is to introduce some of the ways to tackle the grand challenges by using advanced materials. So this is all for me. So I want to start a workshop and Dr. Marco Fronzi, and he has 3 affiliations. So one is University of Technology Sydney, then Xian University, China, and Shibaura IT, because Marco will join Shibaura IT from October. Okay, so thank you so much, and please start your talk.
Thank you very much for the introduction. Let me see if I can share my slide. Can you see?
It's a presenter view, so you can make full screen. Okay, thank you.
Okay, perfect. First of all, I want to thank you for inviting me, for giving me this chance to have part of this talk. And yeah, thanks for the introduction. Today I will talk a little bit about thermoelectric oxides from a computational theoretical point of view. So I will give you a survey of 12 possible materials, novel materials for thermoelectric application. I will repeat a little bit. Okay, I will start with a little introduction. Probably I will repeat myself what Professor Miao Lei just said, but it's, you know, it's a natural overlap. Then I will spend a few slides on the methodology, which I think is important to understand what's going on and the approach that I use. And then I will give you the result and just one slide for the summary. So the Seebeck effect was discovered in 1822, and basically the power of this effect is that, this effect predicts that if you have a hot reservoir and then a less hot reservoir, you put it in contact with 2 materials, you can generate a voltage and a current. The power of this effect, this discovery, is that usually heat is considered to be the less noble form of energy and the last at the chain of the energy, at the energy chain. So to be able to produce energy from what is considered to be a heat is a powerful effect, powerful discovery. However, it was not it was just a physical discovery in the past, but it became important recently when the interest in renewable energy increased recently. Finally, I think it's funny, the Peltier effect, which is actually the reverse of the Seebeck effect, and it's predict that if you have if you impose a current going through two materials, you can transfer heat from a hot reservoir to a cold reservoir. It's basically the same effect, reversed, but it takes 12 years to discover this. As I just mentioned, the power of the Seebeck effect is that we can use heat, which is considered to be a waste, and most of the time it is actually a waste. It comes from many sources, from home industry, background heat, even body heat. Everything can be considered, as long as everything can be considered a source of energy in that sense, as long as we have a gradient in temperature. The other great advantage of thermoelectricity is that there are no moving parts, and therefore there's no maintenance, basically low to no maintenance. Now, conventional, sorry, let me just fix this, okay. Conventional thermoelectric materials include ACE-based compound, half-cluster alloys, cerium-germanium-based alloys. Now, from one side, they can act very well as good thermoelectric materials, but on the other side, they show some shortage, let's say some disadvantages. For example, some of them show lower power density at lower temperature. Some other of them show instability during heat cooling cycle, or low dopability or other toxicity. On the other hand, oxide offer, on the contrary, great stability, low to no toxicity, and high dopability. The problem with oxide is, in general, not always, but in general, is that they suffer from a low Seebeck coefficient if compared to other materials. So that's why we want to, in this study, analyze several the Seebeck coefficient as a function of the temperature of several metal oxide materials. Now, I repeat myself. I repeat what it was just said, but I think it's worth to do it. Now, from like the key quantities for in the thermoelectric effect are the Seebeck coefficient, which is, from a microscopic point of view, can be defined by the ratio between the difference in voltage and gradient in temperature. From atomistic scale, it can be calculated or calculated based on the knowledge of the electronic structure. Now, the Seebeck coefficient is a key quantity, and the Seebeck coefficient can be linked to another key quantity that is figure of merit. The figure of merit is proportional to the Seebeck coefficient, to the electrical conductivity, and is inversely proportional to the thermal conductivity. Now, the figure of merit is related to the efficiency, in a way, to the efficiency of a material. Now, the interplay of these three quantities, it's kind of complex. However, what we are looking for is to have a high efficiency, so a high figure of merit. We want to have a high Seebeck coefficient, high electrical conductivity, and low thermal conductivity. Usually this is reached in the range of semiconductors, as this plot shows. So what we want is to have these three parameters high Seebeck coefficient, high electrical conductivity, and low thermal conductivity. One important parameter is to have high Seebeck coefficient. And we saw that, as I just mentioned, that usually metal oxides show low Seebeck coefficient. Now, this plot shows where we are at the moment with the figure of merit. So we can reach figure of merit around 1. Ambitious would be 4, and of course, there's no limit to that, if not the Carnot efficiency. Now, the typical approach that the experimental people does is the trial and error approach. Now, this is usually cost from money-wise and time-wise. Now, I believe that a computational analysis is worth it to do it because, first of all, it shares light in the basic physics of the mechanisms. From the other side, it can be a guideline for experimentalists because it can be a first screening to reduce cost in terms of money and time. So here I propose, I will show you how 3D and 4D doped spinel iron oxide can reach high, sometimes, only some of them can reach very high Seebeck coefficient, comparable to other more conventional materials used in thermoelectrics, and higher than other metal oxide used currently in this field. Now, I use a density functional theory approach to analyze the ground state of the electronic structure of this spinel compound that I just showed you. I use the implementation effects, which is very, very popular at the moment. And these are just some parameters if somebody needs to know of the computational details that I use, computational setup that I use. Now, the density functional theory gives a very good description of the ground state of metal oxide, and this has been shown for years. However, to study the parameters that are fundamental for thermoelectricity, we need to go beyond the density functional theory, and we have to use the Boltzmann transport theory, which is an approach that allows us to describe a system out of the equilibrium. Basically, the Boltzmann transport theory describes a current as a sum, coming from the sum of each contribution, electrical, magnetic, and thermic, okay, times the relative tensors. Now, from a microscopic point of view, we can calculate those tensors and within this theory, extract the current that we want and extract after that all the quantities that we need. In this case, the Seebeck coefficient. Now, yes, we can derive all these quantities, all these tensors that appear in the Boltzmann transport theory that I just showed you, within the density functional theory. So we do density functional theory, we apply Boltzmann theory, and we extract and calculate the Seebeck coefficient. There is one important approximation that must be done in order to use this approach, and it's called the constant relaxation time. Basically, the Seebeck coefficient is considered to be independent of the scattering of the particles. Or from a different point of view, the mean, during diffusion, the mean path of each particles is longer than the lattice spacing. This is most of the time, this approximation is valid. It's not valid only when the Seebeck coefficient strongly depends on the energy range. But this is true only in very few cases, for example, in the case of lithium, but it's not our case, so this approximation can be considered okay. Now, first of all, from a very basic perspective, Spinel iron oxide, which is the basic structure that we use, and then we dope it. But first of all, let's understand what's going on in the basic structure iron oxide. What we expect, even after doping, is that the structure, the electronic structure, will resemble the one of the magnetite. Okay, which means that we're supposed to see a crystal field splitting, so that the E and the T2 levels will split and will be not degenerate anymore. Second effect that we should be able to see is that the magnetic exchange will make electrons spin up and spin down different in energy and separated. Now, let's go straight to the analysis of the electronic structure of the 3D transitional method doped. So we take the iron oxide spinel structure and we dope with 12 compounds, as I mentioned before. 3 of them belong to 3D. Sorry, 6 of them belong to the 3D, 6 of them belong to the 4D. The TD goes from vanadium to nickel. The 4D goes to from niobium to palladium. Now, let's analyze first the 3D and let's see what happens. First of all, what we can notice is that for all of these compounds, we respect both the crystal field split and the magnetic exchange up and down difference. So, this is a suggestion that the calculations are realistic, like resemble realistically what we expect from this structure. Now, I forgot to say why it's important to analyze the DOS of these materials. It is important because the Seebeck coefficient is approximately proportional to the effective mass of the carriers. So this implies that if we look at the band structure, the effective mass is linked to the second derivative of the band, each band for each direction, which means that if a band is flat, we have a high mass and high Seebeck coefficient. Flat bands correspond in the DOS, density of state, to very sharp peaks. So we are looking for sharp peaks close to the Fermi level as an indication of high Seebeck coefficient. Now, all of those respect what we our expectation of crystal field splitting and magnetic exchange splitting. So the calculations seems to be okay. Second, things to notice that the DOS give either metallic or half metallic compound, with the exception of the manganate, which if you notice, there's a bar, black bar here in the left panel. We calculate to be a band gap there, even if it's small, there is a band gap. But for all other compounds, they show either a metallic or half metallic. What is very important is that there is disproportion between, due to the doping, there is a disproportion of iron +3 and iron +2. Now, the iron +3 up is full and down is completely empty. And this is what characterizes this kind of doped compound. But the dominance of F2 2+ 2G at the top of the valence band indicate that sharpness and distance to the Fermi level can be determinant, can be crucial in determine the value of the Seebeck coefficient. So we are looking at small, very sharp close to the Fermi level, and Fe2+ is crucial to this. We can see pretty much the same dose density of state for the 4D elements, for the 4D transition method. However, here the band gap is much smaller. We still see metallic or half metallic, and we still have one element that induces a band gap. Here is the ruthenium. But all the consideration that we've done for the 3D transition metal doping can be drawn here. So we still F2+ close to the Fermi level are a strong indication of the quality of the value of the Seebeck coefficient. Now, this slide is the core of the work. Once we have the density of state coming from the one that I just showed you, coming from the density functional theory, using the Boltzmann transport theory within those approximations that I just mentioned, we can extract the Seebeck coefficient as a function of the temperature at different doping levels, both N-doping and P-doping. We notice that, generally speaking, there is a strong dependency on the doping level. Second of all, there is a strong dependency on, generally, strong dependency on the temperature. So, which is normal that Seebeck coefficient change hugely sometimes its value at low, for low or high temperatures. However, we found that, this is very interesting, generally speaking, we reach overall decent value for the Seebeck coefficient, but the best performing are the chromium doped and molybdenum doped, which can reach very high, not only very high Seebeck coefficient values, it reached 800, but also that for specific level of doping, the value of S is almost constant, which is extremely good for practical application. So we predict these two compounds to be potentially very useful in thermoelectric application. Also, another interesting thing is that these two compounds show characteristics in terms of Seebeck coefficient that are almost symmetric for N-type or P-type doping. Now, this is to summarize the calculated Seebeck coefficient for this compound and some comparison with other oxide structure found in the literature. As you can see, good performing oxides reach Seebeck coefficient values of 210 or minus 130. That really depends on the sign, depends on the doping. We reach 700 microvolts per Kelvin, which is great considering that range that usually oxides reach. So let's consider these two compounds, these two oxides, and let's further analyze what happened to the other key properties, which are the electrical contribution to the thermal conductivity, the electrical conductivity, and the power factor. Okay. From the band structure shown in the left panel, we can extract by second derivative the electron and hole mass, which is shown in this table here. Now, electron and hole mass here are very, very different, which implies in theory that we can have extremely different property if it's N or P dope. This is in general. However, once we calculate this is in the red panel, we calculated 3 key properties: electric conductivity, electronical contribution to the thermal conductivity, and power factor. We see 2 or 3 main things. First of all, the chromium doped iron oxide show same properties for N doping or P doping. So N doping and P doping are shown in different colors. Okay. Chromium doped iron oxide show very, very similar, almost same properties for the 2 kind of doping. However, the 3 properties changed hugely with the temperature. On the other side, the MOF204 shows very different properties for N-type or P-type doping, but the property almost, they show a very small change with the temperature, which is very useful in practical applications. So we consider MOF204 potentially very good for thermoelectric application for many things. First, high Seebeck coefficient. Second, it works very well at every temperature. And there, I mean, its characteristics are almost constant. Now, it's a theoretical study, so what we want to check is obviously if these compounds are stable, dynamically stable. And we follow the Boltzmann criteria to check the stability. This criteria states that Higgs free energy of a crystal should be minimum if compared to any infinitesimal strain. So we use the strain stress method to calculate the elastic constant and see if there's any discrepancy or any negative value would imply a instability of the compound. Now, in general, the elastic tensor is a 6x6 matrix, but in some cases, due to symmetry, we can reduce the number of elements in the matrix. In this case, we only have 4. We only have 3. The C11, the C12, which is symmetric to the 121 are symmetric, and the C44. We calculate the matrix element and the elastic constant, and we, as you can see in the matrix here, in the table here, all the quantities are positive and actually high value. So which means that our best performing thermoelectric oxide are also stable. Obviously, this is done at 0 temperature. So the stability, the temperature stability has not been checked yet. So this is all for my speech. And to briefly summarize what I just said, I propose a search of novel thermoelectric materials from computational point of view. And I gave you a survey of 12 3D and 4D doped iron oxide. Using a theoretical approach, I compute the electronic structure and I gave you my result in terms of DOS analysis. Using a Boltzmann transport theory, which is a semi-classical approach, we calculated the Seebeck coefficient of 12 structures at different doping levels. And we identified 2 structures with high Seebeck coefficient, which are chromium and molybdenum iron oxide. This structure, and we identified that with this structure have high Seebeck coefficient and low carrier concentration. And for some concentration, it is almost constant. The Seebeck coefficient is almost constant, which is beneficial for thermoelectrical practical application. Yeah, thank you very much. And if you have any question, I'm very happy to answer.
Thank you, Marco, for a nice talk. So, is there any question? So,
excuse me, Paulo, Professor Paulo.
Yes.
This is Miao.
Yes, please. Please.
I have a question. Thank you for the nice presentation. So I want to ask how about the electrical conductivity and the thermal conductivity? Oxide material, commonly oxide material have good Seebeck coefficient, but the electrical conductivity and thermal conductivity are not very well. So I questioned about that two parameter.
The electrical conductivity has been calculated here. Can you still see my presentation?
Yeah.
Sharing the screen, right? Yeah. So thermal electrical conductivity is shown here in the panel highlighted in red. Yeah. Obviously, for the thermal conductivity, we need to add something on the top of this study, which is the phonon dispersion, and what we could do is the same analysis for the apply the Boltzmann theory to the phonon. But we didn't do this yet. We believe that the important part in the discovery of novel materials regarding metal oxides, the important part is this. So obviously, if you want to have a complete study, you should study also the phonon contribution to the thermal conductivity. Yes, this is something that should be done.
Yeah. Okay. Thank you very much. Maybe I missed this slides. Yes. Thank you. Yeah.
Thanks.
Okay. So thank you. Any other question?
Okay, I have questions.
Yes, please.
Hey, anyways, nice to see you guys. I'm Shunli from the South Korea, and thank you for this nice talk, Dr. Marco. And my first question was same as the Miao Lei. But my second question is, why did you choose this spinel structure? Why are you interested in the spinel structure? And another question is, can you do something for the some domain effect, magnetic domain effect in your calculations?
If I can study the magnetic domain, yes, it's possible to study the magnetic domain. But are you referring to this, to the thermoelectric, or in general?
Thermoelectric properties.
Magnetic properties?
No, I mean the magnetic domain effect on the thermoelectric property.
Magnetic domain on the conductivity. Well, yeah, we didn't consider explicitly that in this study. But are you referring to the fact that the spin entropy will have an effect, right?
Yes.
Because this is implicit. The magnetic properties are already included in this study implicitly. So I'm not sure if I answered to your question, but if you look at this DOS, there is an evident magnetic exchange, right? So the magnetic contribution to the total effect is already implicitly included.
Okay.
I'm not sure if I'm answering to your question. Probably. Please.
Okay.
Or maybe we can talk about this. Like,
how about this? Why did you choose the spinel? Why are you interested in terms of this?
This is a survey. Okay, so we just choose iron oxide because we believe that these magnetic alignments and the spin entropy due to the magnetism of this compound can have an influence on the thermoelectric properties. So we started from this consideration.
Okay.
And just just make a survey of the possible doping.
Okay. All right. Thank you.
Thank you, Sonil, for coming and for joining and for the question. So next question is from Otaki Sensei. So Otaki Sensei, could you give your question, please?
Yes.
Thank you.
Thank you very much for a very nice presentation. I think you can simulate, for instance, the Seebeck and also the electroconductivity as a function of the carrier concentration, right?
Can you repeat? I can simulate.
You can yes, calculate the Seebeck coefficient and also the electroconductivity as a function of the carrier concentration.
Yes. Yes.
So then you can do some so-called Jonker plots, which you can simulate, let's say, the change of the power factor as a function of the carrier concentration or as a function of the electroconductivity sigma. Then you can predict.
We've done that.
Then,
and just to be short, I showed you only the best performing carrier concentration. But we've done that, a survey of different carrier concentrations.
So that the highest possible power factor, what was that?
The concentration, the best concentration here is 10 to the 19 per centimeter cube. That's the best concentration of carriers.
Then what was the power factor value at that carrier concentration?
It's in this panel.
10 to 10th? What's the unit? I think it's a different unit as normal one. So it's divided by...
This power factor is divided by the time.
Yeah, time.
Yes, constant. Because we are in the time, relaxation time constant approximation. And we divide everything by that value.
So if you multiply by that with the reaction time, what did the...
yeah, sorry, I don't have the number here. Sorry.
So maybe tau would be 10 to maybe minus external. I don't know how much. So yeah, my question was simple. So if you assume a certain lattice thermoconductivity, actually you can predict the highest possible Z and ZT on assumption of a certain value of the lattice thermoconductivity.
Yeah. So basically, what you're asking is that can you predict the power factor as a function of the some other conductivity, either thermal or electrical?
Yes, because the as far as you can tune the carrier concentration by doping or something. So if you assume the so-called rigid band model, and you can predict how high you can get in ZT or power factor.
Yeah. No. We have
the
power factor as a function of the carriers.
Yes, I know that. So then, but I can't see the number.
No, I don't have the plot. I don't have the plot, but we have a different carrier concentration. What happened to the power factor?
Okay, then that's how promising these Spinel type oxides.
Well,
how do you think?
No, in this sense, I don't have a survey or a direct comparison with the literature. But the focus, because the weak point of metal oxide is the Seebeck coefficient. So we focus mainly on the Seebeck coefficient, and we found that the Seebeck coefficient of a couple of structures is higher than conventional metal oxides used in thermoelectrics. So this is what we focused on mainly. Yeah, of course. I'm not saying that these.
Yes. Okay. I can change my comment. So actually, my opinion is that the weak point of the oxide is not actually this low Seebeck. Actually, it's low carrier mobility, which leads to the if you wish to gain the high electrical conductivity, of course you will dope the carriers, and then the decrease in Seebeck is rather steep than other things. That means the carrier mobility is low. So you can get the high, how to say, Seebeck coefficient easily if you decrease the carrier concentration. But actually, the compromise between the S and the sigma is more severe than other materials in general. That is, I think, because of the actually low carrier mobility. So we need something to overcome that weak point if you wish to find the good oxides. And it's not so easy because the normal oxides, like for instance the tin ITO based one or other things, can can be very good conductor. But as I said, the compromise between the Seebeck and the sigma is still severe. Yeah. So
that may be the weak point.
Yeah, basically it's based on the I just show the bond structure of the oxides and the actually the band duality is not so, as I say, the wide. So that's my comment. So then from your standpoint, what you can suggest, how we can overcome such, how to say, very more severe compromise between the Seebeck and the electroconductivity.
That's something I need to think about, but it's a good point. Yeah.
Okay, thank you very much.
Thank you.
Okay, thank you for everyone for this very nice discussion. So we have to move on to the next talk. The next talk from Dr. Deva Arun Kumar from Shibaura Institute of Technology. So Dr. Kumar actually now is stuck in India. Unfortunately, he was expected to join my laboratory from April, but due to the situation you know very well, so it was not possible, not yet. So I hope he can join SIT and enter to Japan very soon. So thank you for joining this workshop, and so please give us your presentation. Thank you.
Hello.
Hello. Yes.
I'm audible, sir.
Yes. So please go ahead.
Yeah. Okay. Good morning to all of you. Actually, I'm Dr. Deva Arun Kumar. I'm doing my postdoc research. Actually, sorry for that. My background is not clear. Some power problem is in my hometown. So I thank you very much, Professor Yellow Mele, for giving this wonderful opportunity for delivering my presentation. And today I'm going to discuss about that feasible thin film preparation techniques for energy materials. So these are the outline of my today's presentation. Sorry. Sorry for the mistake. Yeah. Okay. This is the outline of my today's presentation. First of all, the introduction of thin film and its uses, and transparent conducting oxide. What is transparent conducting oxide? And aluminum doped zinc oxide. What purpose of using for THTCO material? And then already I told the feasible thin film techniques like chemical based deposition techniques. Here we are going to discuss about that. And then finally, but my results and conclusions, and then current work, what I am doing now, like that. So this is a thin film. Thin film, it's a thin layer of material which is a range of thickness in the fraction of nanometer to several micrometer in thickness. So we can identify 3 types of thin film. Why it's changing the thickness range. So the thickness is below 100 nanometer is ultra thin film. It should be in the range of 100 nanometer to 1000 nanometer or 1 or 2 micrometer. It's called as thin film. So above 1 micrometer or above 2 micrometer is called a thick film. So what thin film compared to bulk material, thin film may not fully dense, so it has minimum stress and it may prepare to different kind of nanostructure like nano rod, nano seed, nano wire, like that. So it enhance that electrical property of the material. So we can prepare 2-dimensional layer. Actually in thin film we can prepare 2-dimensional layer like X and Y direction. So it strongly influenced by the surface and interface effect. So this will change the properties, some properties like electrical, optical and mechanical properties, some structural properties and so on. And purpose of thin film, thin film to maintain surface uniformity, and it reduces that amount of light absorbing material, and it has used the spray coating technology for functional medical coatings to decrease that weight of the material, to decrease the thickness, like weight of the material. We can prepare as a glass slide like that. And then thin film technology. So thin film technology involves some deposition of individual molecules and atoms. It requires to control thickness of the thin film by varying deposition methods or as uses in today. So different deposition method have a specific limitation with respect to change of different parameters. And then thin film application. Thin films generally thin films used in many optical as electrical device applications such as solar cell, photovoltaic, like thermoelectric device for energy harvesting application, and for sensor, many sensor like gas sensor, and then photo detector, then photocatalytic degradation, like that. So and so on. So thin film photovoltaic, mainly thin film are used in solar like photovoltaic and tissue as a tissue material in aluminum doped zinc oxide, like that. So the thin film photovoltaic is an second generation solar cell. First one is amorphous silicon. So these are 2 main categories to be considered before the choice of crystalline semiconductor. So one is that should be in the crystalline silicon wafer form in the range of thickness micrometer to nanometer. Sorry, micrometer to millimeter, and then it should be on thin film like nanometer to micrometer in the range of thickness. So there are 3 key elements to form a solar cell, like solar cell. One is that the material should be is a semiconducting behavior which absorbs light and convert into electron hole pairs. So second one thing is the semiconducting junction. We just focus the semiconducting junction which separates that photo generated carriers like electron holes. So third one is it should be the contact, front and back contact, like electrodes, and that electrode which involves to allow the current to flow the external circuit. So thin film solar cell, the requirement of DFSC like thin film solar cell is optical absorption and doping. Doping can enhance the electrical properties, some impurity atom by into the host material. So electron transport mechanism as well as increasing, and then stability of the material, it should be good for thin film solar cell. And that there are leading material for making thin film solar cell like cadmium telluride and copper indium selenide, copper indium, gallium selenide, and amorphous silicon. What are the advantages? Advantage, it's a low material requirement, variety of processing method is there, and currently the many people are working thin film solar cell, and this is lightweight model. We can prepare lightweight model. And the only disadvantage is to achieve very low efficiency. Nowadays people are achieving good efficiency, around 22% of efficiency. Nowadays people are working from thin film solar cell. So another application, main application is optoelectronics. Optoelectronics, light involves some electron movement with transparent substrate, within a transparent substrate. These are the uses of optoelectronic, like LED display, and then solar cell like electrode flat panel displays, and so on. So TCO thin film, so transparent conducting oxide. The oxide material should have highly transparent in that visible range, and then it has low electrical resistivity or good electrical conductivity. It's called as the TCO material, like transparent conducting oxide material. So in that TCO material, the band gap should be greater than 3 electron volt. So it should be avoid that absorption in the visible region. So requirement of TCO material. So what are the requirement? There are two main requirements. One is the transparency, another one is the electrical resistivity. The transparency should be above 80%, and then resistivity should be in the range of minus 10 to the power of minus 3 or 10 to the power of minus 4 is good for TCO material. There are many TCO materials are there, like indium oxide, cadmium oxide, and tin oxide, zinc oxide, and so on. So here, indium oxide is one of the expensive material compared to these mentioned other material. So cadmium oxide is already, we know that it is the toxic material. Then tin oxide, it can change the phase, like tin oxide, tin dioxide, like that, SNO, SNO2. But still, ZNO is a stable one material like zinc oxide. So it has a low cost material. So here I have chosen zinc oxide is good for tissue material. These are the two images before coating, after coating. Left side one is the glass substrate, and right side one is the tissue after preparing thin film. Actually, these are actually these both are seems looking same. So it can call as the tissue transparent conducting oxide material. So zinc oxide is a familiar semiconducting material, group 2,6 semiconducting material. The band gap should be high, 3 white band gap 3.3 above electron volt, and the binding energy is high at 60 milli electron volt, and then it has a hexagonal oxide structure. So the zinc oxide, the lattice cell parameter value A and B not equal to C. So A and B both A value and C value is 90 degree, and C is that 120 degree. So A and B is same, and B is not equal to. So in that case, zinc oxide, usually zinc oxide has a high resisting material, but in that case, if we prepare a TCO material, we should improve that electrical property. So in that case, we just include some impurity element into the zinc oxide. So these are the element, doping element, like group 3 element is best to opt-in for that zinc oxide material to improve the electrical performance. So these are the group 3 element, like indium, gallium, aluminum, barium, like that. So here, indium and gallium is a expensive material. So the only option is aluminum is very low cost, which gives a good electrical performance into the zinc oxide material. So types of thin film deposition method. There are two main types of thin film deposition. One is physical vapor deposition, another one is chemical deposition. Like physical vapor deposition, which means a solid material can directly vaporize onto a substrate, finally into get thin film. In that chemical deposition, the liquid solution, with liquid solution, the reaction of the chemical by applying some heat purpose to get thin film. Here, chemical method, we should use some solvent like water, ethanol, like that. In that chemical deposition is very low cost compared to physical deposition. These are the physical deposition like thermal evaporation, active, reactive, and so on. Already we know that about that. So in that chemical, so what are the chemical deposition? Like electrode deposition is there, and the salt gel deposition like spin coating, tip coating, and sillar like successive ionic layer adsorption and reaction method. One is a chemical bath deposition method, and another one is spray pyrolysis, and the final one is hydrothermal, and etc. Many other for using chemical deposition method. So first one, we are discussing about first one, like a chemical path deposition. Chemical path deposition is a very low cost method to prepare thin film with the different nanostructure. What is the chemical? It involves the control of precipitation to form on a suitable substrate. Here we have used only as magnetic stirrer and some beaker. That is enough for this method, preparing thin film with some different kind of nanostructure. So here we used here we can change different deposition time to prepare thin film, different kind of thin film. So in that case, after that, after prepare the thin film from this one, here this. So this one is magnetic pellet to agitate the solution. It can be used to induce that electron from that solution to form a substrate. So these are the parameter of preparing chemical path deposited thin film, ZNO, aluminum doped ZNO thin film, and this one is the extra-posted thin film. After here, I changed for different type of deposition time for making four thin film, and the extra-posted isotope thin film. Finally, it has been annealed around 500 degrees Celsius for 1 hour. What is the purpose of annealing? The annealing it can improve that uniform arrangement of atom on the substrate. So these are that X-ray powder diffraction. So here we can see that by increasing that deposition time from 20 minutes to 80 minutes, that peak intensity, the XRD peak intensity of 002 plane is considerably increasing. It was reached up to 60 minutes, it was reached up to maximum intensity to do with this that which is confirmed by that high crystalline quality in this material. Above what beyond that 80 above 60 minutes, it can some kind of precipitation are formed. You can observe in that semi image some holes porous nature also present in that film surface. So in that case, that film crystalline quality is slowly reduced for higher deposition rate. So the main reasons to form a precipitate form. So here is the transparency. The transparency it's obtained around 87% in that near visible range, and then band gap also confirmed 3.25 electron volt. So here that resistivity and carrier concentration mobility, though the resistivity is considerably decreasing up to 60 minutes because the increase of carrier concentration to do that crystalline quality, depend upon the crystalline quality. After 80 minutes deposition, the resistivity are increased, little bit increased due to that precipitation, form of precipitation already I told. Then next one is Shiller method. So Shiller like successive ionic layer adsorption and reaction method. So these are the schematic diagram of Shiller method, which we have considered five main steps to prepare Shiller thin film. These are the 5 methods. So first one, peak area just condensed in zinc prepared solution. Second one is just hot water, like H2O water. And then next one is ultrasonic water, and fourth one is like peak D is ethylene glycol solution. Ethylene glycol, why here we are using ethylene glycol? Because the ethylene glycol is act as a dispersing agent. It can remove that zinc agglomeration, some unwanted zinc agglomeration, it is reduced. So removed from the substrate. Finally, we just put inside that ultrasonic water to remove the stacky form of the ZNO, and this process can repeat to get several times to get desired film thickness. After once we prepare this thin film, we can go for the annealing. Annealing already told, annealing it can convert to uniform arrangement of atom on the substrate. And these are the thin film prepared, Shiller prepared AICTO thin film, like aluminum doped ZNO thin film. So from here I changed 4 type of precursor, zinc precursor, zinc nitrate and zinc acetate, zinc sulfate and zinc chloride precursor. So from change S1 to S4, like zinc nitrate to zinc chloride, that peak intensity should be increasing to decreasing of fluid top maximum value. Here the maximum intensity is obtained for zinc chloride precursor, which implies that high crystalline quality of the material. So here for zinc nitrate, here each Shiller method is very unique for preparing different nanostructure. Like here we observed some zinc nitrate, zinc acetate salt. Here we observe like flower like formation of zinc oxide thin film. this kind of structure can improve the electrical performance. So after that, we just obtain some spherical shaped grains. So this kind of all the grains are almost interconnected each other. This kind of nanostructure can enhance the mobility, because that the electron can improve from one grain to another grain. So the mobility can be increased to increasing the conductivity also can be increased. So these are the transmittance. It shown some maximum in the transmittance. It shows some maxima and minima. So some maxima and minima. This is implies to the high crystalline crystallinity of this material. So as per the previous slide study, the zinc chloride precursor has a good crystallinity. So it is also suggest for that result. So here we observed around 90% of the transparent in the visible spectrum. So here also that band gap should be around 3.21 electron volt. And these are the photoluminescence. So PL intensity. So first high intensity PL peak is expected. This is the near band edge emission, like band gap. It's very near to band gap. So this is what comes from the recombination of electron and hole pairs from the valence band to conduction band. And the next one is the low intensity. This is the like impurity, like Oxidation effect or zinc interstitial position, which is around. So this band gap, this NP emission, which is very near close to our obtained band gap of the material. So this is resistivity. Already I mentioned that different nanostructure can enhance the mobility of the material. So speed of electron. So in that case, the mobility also increased up to sample 4, like zinc chloride precursor from zinc acetate. Here we already mentioned some of that. Some of the porous nature are interconnected, not missing here, not missing the interconnector. So here observed the low mobility of the material. So this one is why ASO2 has low resistivity, because this is the mechanism. So the aluminum ion can the low ionic radius of aluminum ion can easily incorporated into the zinc site. So as a result, increase that electron free, it can donate free electron to the Jiaotong circuit, Jiaotong structure, and then that some of the zinc is act as interstitial position. So it can also enhance that carrier concentration of the material. So here for chlorine, for chloride, zinc chloride precursor, we observed low electrical resistivity and high carrier concentration. The reason is that the substitution of chlorine ions into the oxidation site of the Jiaotong. So it can produce more charge carriers. So this one is the electrode deposition method. So in this method, same as that chemical path. Previously we saw that chemical path method, same as chemical path, but here we should use some working electrode is like conducting material. All the other material we can use some amorphous substrate, say porous liquid substrate or some amorphous substrate. Here we should use some electrode like conducting substrate. So this is the electrode deposition. Here what is the function? Electrode deposition involves some dissociation of metal salt into anions and cations. So here also same as per that chemical path deposition, but in the only difference is here we should use some electrode. Like here I am using working electrode as a FTO, and the other electrodes like counter electrode and reference electrode are same for all the measurement. Like counter electrode is a platinum wire. It can induce the electron from the solution to deposit on that substrate for the function of both two electrodes. It should be give some voltage from that Kitli source meter. So already I told here I used a conducting substrate like F2O substrate. So in that XRD spectrum, the observed here I identified some star peaks. Now, these peaks are corresponding to SNO2 structure because I used F2O. So this is SNO2 structure, tetragonal structure. once I increase that potential voltage, the SNO2 peak intensities are decreasing considerably. On the other hand, the 002 plane ZNO should be enhanced. So here the maximum crystallinity of the material is obtained for minus 2.51 voltage, applied voltage for this electrodeposition method. This is the SEM image. It can observe from some seed-like nanostructure from that SEM image. And these are the elemental composition. We can confirm like zinc oxide and SN. Aluminum and tin oxide, which comes from the F2O glass substrate. So when increasing the potential, that band gap also decreased because increasing the thickness of the material. So here is that electrical resistivity here is obtained for the maximum crystallinity, obtain low resistivity, which is to the maximum film crystalline quality. The transmittance up to the transmittance here is around 80%. It little bit affected due to we are using already F2O substrate, so it can affect the transmittance of the material. So the band gap also very low for like around 3.1 electron volt, and the resistivity also bit low compared to other methods like 10 to the power minus 2 ohm centimeter. Photoluminescence already we discussed. Photoluminescence is the same actually 386 nanometer for the NP emission, and then 522 nanometer it comes on the defect like zinc industry cellular acquisition deficiency. And these are the another method and to prepare salt gel. So prepare salt gel preparation. So salt gel method. So we should use some kind of different solvent. So here I choose the different kind of alcohol like 2-methoxyethanol, isopropyl, propanol, ethanol, and methanol, because these 4 solvents have different kind of density. So in that process of converting liquid into gel formation, it can change that parameter by its depending upon the densities. So here these are the chosen of different kind of alcohol for salt gel method. This is the salt gel tip coating method. So for converting liquid into gel formation, that stabilizer agent, we should use some stabilizing agent like monoethanolamine, triethanolamine, diethanolamine. So it can act as a stabilizer agent. It is used to convert liquid into gel formation with some temperature, applied temperature. So here I choose same ratio for both MEA like monoethanolamine and zinc. So these are the tip coating method. So just two process, only two process. One is zinc solution. The second one is tube furnace. Zinc solution we just tipped in the substrate into the zinc solution, and then withdrawal speed is very low. See 5 centimeter per mil, which is controlled by the microcontroller, some programmable microcontroller. And then second one is tube furnace. Tube furnace, why we are using tube furnace? The tube furnace around 20 to 280 degrees Celsius tube furnace, it can use to evaporate the solvent. The unreacted solvent, it can use to evaporate. So this process we can repeat for several times for getting desired film thickness. After finish this process, we just annihilate for the film at required temperature, like 500 temperature. Here I used 500 temperature to get uniformity of the film. So these are the XRD spectrum. Here observe the XRD spectrum for methanol solvent is high crystalline quality to low beta value. So in that case, for different solvent has a different kind of nanostructure from semi-image like carbon structure, some nanorod structure, needle-like structure. This kind of structure can improve that. Already I told chemical method can be used to prepare different kind of nanostructure. We can prepare like flower-like structure, nanorod-like structure, nano shape like nano sheet-like structure. Say here also we are preparing some different kind of nanostructure. So here methanol is the high crystalline quality to do that. It has some lowest surface energy. So these are the transmittance. The transmittance also it comes around average transmittance for four thin films like 85%. That band gap also the same, which implies that wide band gap of Z2 material. So these are that electrical table. So here is the thickness of that material, which is changed from 272 nanometer to 44.3 nanometer. So it has confirmed the thin film thickness is a bit low. So 272 is a bit low. So in the resistivity, it has absorbed the low resistivity like for methanol solvent sample D, like 7.56 × 10⁻³ ohm centimeter. So carrier, because it has good carrier concentration, and then carrier mobility also decreasing to with respect to change of different nanostructure. These are the same salt gel method. This is a spin coating method. So here I used the same method to prepare the salt gel solution. Then finally I just kept into aged solution, kept at room temperature for aged solution 48 hours. So for aged solution, it can use to remove that solvent evaporation. It can use to solvent evaporation. This one is that spin coating, like arrow mark is that spinning process is 300 rpm and 30 seconds, and then it has also repeated for several times to get desired film thickness. After getting that film, it has used to annulate for 200 degree and to finally to get thin film. And these are that XRD. Here also we get the same solvent I used to do, which I have used to for tip coating method. So methanol, ethanol, and isopropanol. Here I got isopropanol, had isopropanol and ethanol, same for that properties. And then annealing induced creation of 002, because of the main fact is salt gel method. Annealing is the main fact. So in that because we are preparing at room temperature for salt gel tip coating and both spin coating also. In that case, many of the solvent cannot be evaporate from the substrate. So in that case, you just go for that annealing. If you are using annealing more and more time, we can get good kind of thin film properties. So here I use 2 hours. If you go for 3 hours, 4 hours, we can get good properties, electrical and optical properties. This transmittance also the same, like 90% that visible range. Resistivity also bit low compared to tip coating method. The resistivity, because here I used to do 7 layer, and tip coating method I used only 5 layer. It may change depend upon the increasing layer. So here I got 1.90 10⁻³ ohm low electrical resistivity compared to other previous method, spin coating method. So crystallite size in the calculator from scalar formulas, calculated crystallite size 40 nanometer, and the band gap 3.15 electron. Transmittance it's around 87 nanometer. So this is the final method, which is called nebulizer spray pyrolysis method. Which one is the very finest method to prepare uniform thickness of the film. Which is very challengeable to physical deposition method, like other method, like already I have discussed in physical deposition method. So from compared to other method, we can prepare very uniformly thickness orientation of the entire substrate. So here main parameter is the nebulizer. Nebulizer is the instrument. It is used to convert liquid into one aerosol. Aerosol, which means aerosol is nothing, is that suspension of small particle. The converted small particle is going inside the tube and then sprayed on a hot substrate. So spray is nothing, thermal decomposition of the particle, suspension particle. So here we just set it automated nebulizer spray method. So the substrate temperature here I kept from previous method. We just prepare room temperature thin film, and finally we got annealed at around 500 or 400 degree. Here we just prepare at 500 to 450 degree temperature. So no need to go for further annealing temperature. The deposition temperature is enough for making Z&O or any oxide material. 450, 400 is enough for any oxide material. So these are the preparation. Here I chosen two kind of solvent. One is water and another one is methanol. So water methanol densities differ from each other. So here I used four step that mechanism of spraying solution, 4 step. Step one is droplet size. So left side is water solvent, right side is methanol. So that the droplet size should be high for water solvent, like 0.5 micrometer to 2 micrometer. So the methanol solvent droplet should be low because the density of the water already high compared to methanol. So in that case, step two, the methanol droplet size considerably reduces compared to water droplets, because the methanol evaporation rate is significantly higher than the water when it is closely reached to the substrate. And then third step is the methanol, all the methanol solvent solution, like a form of mist, and then it is reached fully on the entire film substrate. But in that left side water solvent, only one steps are uniquely, it has absorbed only one step. The thing is, some of the solvent tends to scatter before the decomposition of the substrate. So it hence unable to form a smooth and defect free, because some of the electrons can scatter from that through that evaporation of solvent, scattered solvent. So in that case, compared to water, methanol can get good structural, optical, electrical behavior. So as per the same, here I mentioned S1 to S5, like S1 from S1 higher water content, S5 methanol content. So here I considerably increasing the methanol from 2 ml to 10 ml. So for fifth sample S5 methanol solvent, 10 ml of methanol solvent has highest crystal structure, like crystallinity, like 52 nanometer. And then the lattice cell also, it is very close to the bulk material ZNO lattice cell, 3.2 and 5.09, like that. And these are the SEM image, FESM image of pure methanol solvent, like sample fifth methanol solvent. This is, look at the sample. This is this SEM image is very close to the commercial F2I2O SEM image. You can refer from other result. And then these are already I told, some of that roughness are increased for that surface roughness are increased for water solvent compared to methanol. So here sample S1 to S5, here that the roughness, smoothness of the film is increasing. Sample A to E, like S1 to S5, the roughness, surface roughness is low, is increasing from sample 1 to sample 5. For sample 5, here we mentioned E. This is as a very low smoothness of the, very high smoothness of the film, which implies to enhance the crystalline quality and also improve the electrical properties. These are the thickness of the film, which I have observed around 800 nanometer for that film, for that desired film. And these are the band gap. So band gap, which around very close to bulk band gap material, or 3.3 electron volt. And then the transmittance spectrum, here we see transmittance spectrum from sample 1 to sample 3, that already we discussed, no, the smoothness is increasing that solvent, methanol solvent. So here we observed for sample 5 that transmittance is very high, like around 93% in that entire visible range. So here also we observed some maximum minima. It implies also the maximum crystalline quality of the material. So these are the XPS spectra, which is confirmed by the 2p orbital in zinc and oxygen and aluminum. So here I just prepare the photodiode. Finally, I conclude that 6 deposition method. Nebulizer is the best method because it has give high transparency and low electrical resistivity in the range of -4 ohm centimeter. So here I came to conclude a nebulizer spray prepared thin film is a good challenging method to compare other chemical methods, not physical method, other chemical methods. So here I prepared some photodiode. using ITO, and copper oxide is a P-type material, and AISO is an N-type material, which I have prepared here in this present work. So this is the current versus voltage studies, the phototier study. It displays the illuminated current level for both forward and reverse biases are very high compared to the dark values. So after that, I just measured the sensing response, photosensing response with respect to time using 200 watt halogen lamp. So in that case, this is for the sample fifth, like methanol solvent fifth, methanol solvent prepared AISO thin film. In that case, the on current is almost 3 order higher than that up current. Like this is -9 to almost reach -6. So 3 times higher than that up current. So it was used as a good sensing behavior of photodiode. So conclusion, when I came to know about the conclusion, so I have used different 6 type of electrode methods, like electrode deposition, chemical partial or sol gel, and spin coating, tip coating, nebulizer spray paralysis. Compared to other methods, nebulizer spray method, it gives highest optical transmittance and low resistivity, 8.69 to the power -4 ohm centimeter. So I found that nebulizer spray is the best way to prepare transparent conducting aluminum doped zinc oxide thin film compared to other chemical methods. So these are the publications, and current work is processing. Thermoelectric, actually many scientists are working alloy material for making TE model, thermoelectric for energy harvesting. And some of the disadvantage I have found. So alloy material usually is not unstable in air, and it can decompose, like it can oxidize quickly. Then oxide material, so oxide material known as gifted material for thermoelectric, because it's more stable in environmental condition at the high temperature also. So bulk material have some disadvantage. Long time for it may not give long time for sintering process. It takes long time. Then it may not prepare some P-type and N-type elements. The arrangement of device shape is not good for bulk oxide material. So we can choose, in that case, we can choose oxide thin film based material. So oxide thin film offer many advantages compared to bulk oxide material, such as it can quickly fabrication. It can fabricate very quickly. Then it may be prepare some flexibility with different type of substrate. Then control defect, and even though it can prepare nanoscale range from thin film, oxide thin film. And so in the recent to best of my knowledge, I'm not sure about it. Recently, the performance of AISO by hydrothermal method, and the reported values 0.28 figure of merit. So I'm not sure about it. I just refer. So these are the collaborator of my entire research. I thank all the collaborator of mine. So thank you.
Thank you so much for a very nice comprehensive talk. Is any question from the audience? Okay, so I have one question myself. So you show many techniques for the chemical deposition, and you conclude nebulizing pyrolysis is the best one.
Yes.
In terms of performance of the film. So may I ask you if you consider also the cost of the technique and the time consuming, which is the best technique?
Actually, cost-wise, this one is the higher cost compared to other. I have discussed about other methods. Actually, here we need some air compressor, like some automation programmable setup, and then controller, temperature controller. Here we should need. So in that case, around 30,000 we have to spend for make this setup to prepare uniform thin film. Around 30 to 40,000. Other methods, it's very low. Actually, in a chemical path method, it is just you can use one magnetic stirrer and then one peaker. That is enough. Similar method also the same. So for this method compared to others, this is bit expensive. Like around 30 to 40,000, we can make on technique for nebulizer spray method.
Okay. Thank you again.
Thank you.
So, if there are no questions, we should pass to the next talk.
Okay. Thank you, Professor. Thank you for giving these opportunities. Thank you. We'll meet you soon.
Thank you so much. Bye.
Thank you.
So next speaker is Alicja Klimkowicz from Shibaura IT. So Alicja, please. Thank you.
Thank you very much, Paolo, for your kind introduction and invitation to this workshop. And I really appreciate you organizing it, so thank you. And now, please let me change the topic a little bit. We learned a lot about energy materials now, and I'm related to it, but yeah, let me explain in which way. So now I will present for you my research work which regards oxygen production and storage using ceramic materials. So first of all, a quick reminder where we use oxygen in the industry. So mainly we use it in a steel industry and also for the production of some chemicals, but also in welding. But for now, probably with the situation unfortunate with the pandemic, we all appreciate the role of oxygen for the medical use, right? But also as a anecdote, I found possible use of oxygen as recreation. So apparently in US there are oxygen bars where you can actually breathe in just pure oxygen. So to use an oxygen, we need to produce it. So for the large scale, we normally use oxygen produced via cryogenic distillation method. But there are also some alternative methods like pressure swing absorption or temperature swing absorption or using ceramic membranes. So I will be talking a little bit about those oxygen production methods in the lecture today. And I will be talking about oxygen production and storage. So now a little bit briefing for the oxygen storage technologies. So as you can see in the screen here, we can distinguish conventional methods and alternative methods. For the conventional, I'm sure you all know liquid oxygen or pressurized oxygen. And you are probably familiar with those storage techniques. The alternative is to use materials for storage. So for example, we can store in a bulk or on the surface, like in the case of zeolites. So for today, I'm gonna present for you use of ceramic oxide, which in shortcut we call it oxygen storage materials. And one disclaimer, as Paolo mentioned in his introduction talk, doesn't matter which technology we use. All of it, it has to be safe, efficient, easy, environmentally friendly, and also for the economy, it has to be cheap. So it also includes the oxygen storage materials. They also need to satisfy those criteria. So let me first define you oxygen storage materials, because I'm pretty sure that this is a new group or new type of materials for you. So basically, we can call material an oxygen storage material if it can reversibly incorporate and release oxygen into or from its structure. So we are talking about the bulk now. And also, this reaction is correlated with the change of oxidation state of at least one of the elements. So here you can see mixed oxide ceria zirconia, in which cerium is changing its oxidation state from +4 into +4 +3 mixture and release appropriate amount of oxygen. So this is very characteristic. This redox reaction in here is very characteristic for oxygen storage material. So a little bit more of the characteristic for the good oxygen storage material. So as I told you, we need to have oxygen that is going to be incorporated into the structure. So we want this amount of oxygen to be large. So we call it large oxygen storage capacity. Also, the speed of this reaction, both intake and release, has to be fast, right? The materials, of course, need to be stable, both chemically and thermally in the working conditions. The operation for those materials, the temperature of operation should be relatively low, but also it depends on the actual application. And of course, material has to be inexpensive, both for production and operation, and environmentally friendly. So I prepared for you here a short summary of, well, only a few compounds that are recognized as oxygen storage materials or oxygen storage systems. So first of all, the Ceria zirconia material that I mentioned before, if we substitute zirconium for lanthanide, those two materials were firstly introduced as oxygen storage materials, and they are used already for probably over 30 years. Then you can see here another materials, and with the ones that are underlined in here in a frame, I will be talking about them today. But let me quickly compare. So you can see that oxygen storage material can exhibit different type of structure, but all of those structures are kind of layered structure. So this seems to be important feature of oxygen storage material. Defined before oxygen storage capacity, you can see we've got different range of oxygen storage capacity, but it's usually around 2 up to maybe 4 weight% of oxygen per mole of compound. Yeah, I'm sorry, weight%, of course. And also the important feature is the temperature of oxidation and atmosphere of oxidation, and symmetrically temperature of reduction and temperature and atmosphere of reduction. So you can see this is the temperature of operation that I was talking about. The different system exhibit different temperatures of operation. So for example, for this brown millerite material, it reduces in 700 Celsius. So to release oxygen, we need 700 Celsius, which is a little bit much. Yeah, so we want material that kind of has moderate temperature, both for oxidation and for reduction. Yeah, so that's why I was focusing my research on those two groups of materials. What is different between them? You can see that in case of here, double perovskites, for the reduction, we need to use reducing atmospheres, while these hexagonal materials, for the reduction, they use, we can reduce material in oxygen-containing atmosphere. So those are two basic differences between those two materials. And I will be talking about that a little bit more further. But before I go into differences, let me talk about similarities. So here you got chemical composition for both of those groups of elements. You can see that they both contain oxygen, with the delta indicating oxygen non-stoichiometry. So this is this oxygen that we can incorporate or release from the structure. The materials that I will be talking about today, they are both based on manganese, but we can change, of course. We can move throughout the 3D materials, because the redox reaction, it's gonna occur in here. So this is in that case, manganese is gonna change the oxidation state to allow oxygen into the structure. Also, the materials I'm talking about today, they are lanthanide base. So basically, yttrium base with some amount of lanthanized rare earth elements substituted. And in the case of double perovskite or ordered perovskite, we usually base them on barium. Yeah, but today I will show you the changes in the LN. So please take a look in here. I will be showing materials of different chemical composition. And by this, I will try to show you how chemical modification can improve the properties of the material. So before I do that, I want to show you, like, very briefly, very schematic view of what is happening in the material during absorption and desorption of oxygen. Pay attention that this is bulk process. So we've got a bulk material, and in the reduced form, there are the layers representing layers of manganese or lanthanide cations, and there is no extra oxygen. Yeah. And then in the absorption process, the oxygen start to be incorporated inside of the material until we reach the fully oxidized material, oxygen loaded material. And we can reverse this process and desorb oxygen. But how do we control it? What is the force behind the absorption and desorption of oxygen? So we can control this process using two methods. We can either use temperature swing or pressure swing. So let me describe the pressure swing, the temperature swing first. So you can see that for this type of operation, the oxygen partial pressure remains constant. And in here, in the very schematic view, you can see that we've got oxygen storage material here in the, well, let's say container, or it's an absorbed bed. And here we've got another one. And the process is cycle in nature. So in the sense here, we've got a production, and here we've got a regeneration step. So in the regeneration step, the air is flowing through the material is absorbing the oxygen, and depleted air is taken outside. Yeah. And then in the production step, the depleted air is going through the material, and we receive enriched air. So if we repeat this process many times and we conduct those cycles many times, we can actually obtain pure oxygen. And so it shouldn't be temperature constant, it should be this one. I've got the labels on the other side, sorry. So for the temperature swing processes, the regeneration step and production step occurs in different temperature, but we keep the oxygen partial pressure constant. So as you can probably guess, for the pressure swing process, we swing the pressure. So we change the oxygen partial pressure, and we keep the temperature in constant. But effectively, the process is very similar because we also work in the cycles of absorption and regeneration. So in general, in the literature, we can divide the oxygen storage material in two groups. The one that works well under pressure swing condition with the constant temperature, or with the temperature swing and with the oxygen partial pressure constant. And today for you, I'm going to show you an example of TSA material, temperature swing, and pressure swing material, this one. So let me start with the pressure swing PSA material. And here is actually the crystal structure of this double perovskite. And as I showed you in the schematic view, this is the reduced material, and you can see here there are the vacancies in which oxygen can actually be absorbed. So in the absorption process, you can see that first half of the position is taken by oxygen, and when we introduce more oxygen, we actually fill up the structure, and we've got nicely ordered structure with all of the oxygen vacancies occupied by oxygen. Yeah? So effectively, there is no oxygen vacancies anymore. And you can see here the change of oxygen is between O5 and O6 for this kind of material. And what is important that this process is reversible, and there is the framework of the material. As you can see here, the framework is preserved. Yeah. So how this material works in practice? So for you that who are not familiar with this experiments, I'm using thermogravimetric machine to measure the weight change of the material during changing of temperature and also gas atmosphere in the chamber. So what I've got here for you today is that those double perovskites, these materials, depending on the Ln cation that was introduced into the structure, show different properties. So what we can observe in here, we start from the reduced material, and then with time in the air atmosphere, the material starts to absorb oxygen, therefore the weight is increasing until the material oxidizes fully, and we've got an oxidized form. You can see that this process is kind of fast. It's in order of seconds. And we end up with the material with oxygen stoichiometry 06. And then if we want to reverse this, we need to change the gas into, well, reducing conditions. Yeah? In this case, it's 5% of hydrogen in argon, but it can be also different gases as long as it's reducing. In argon, it will also cure, but it will be very slow. But what you can see here, that oxidized material in such conditions will release the oxygen until it reaches stable stoichiometry of oxygen 05. And another important part is here that this process is not symmetrical, because the reduction or oxygen desorption, if you will, actually takes minutes. So oxidation is much faster than the reduction. So in my studies, I was trying to improve this reduction process. And as you can see, different compositions, different substituted lanthanides show different behavior. With the best one, gadolinium-containing sample that reduced twice as fast as the parent yttrium-containing material. So with the chemical modification, we can actually greatly improve the properties of such materials. And now, as I told you, that those materials or work of this material is cycle in nature. So in here, I show you 50 cycles of consecutive reduction and oxidation. And to show you the stability of such process, we can actually really obtain the once achieved at the beginning capacity, and it works very stably. Here you can see it for optimized chemical composition of yttrium-75, praseodymium-25. Another thing that I want to share with you today is morphology modification, because there is only so much that we can do with the chemical composition, but modification in the morphology can also yield good results. So in here, the SEM pictures of praseodymium containing sample, which is non-milled just after sintering, and here material that was additionally just mechanically milled. You can see the increase in the decrease in grain size. And actually, we tested different types of milling. As you can see in here, we have as-prepared sample. This is XRD results showing just the selected peak range. But you can see here that with the increase of milling time, the peaks are actually broadened. Yeah, so this means that the crystalline size is increasing in the material. Unfortunately, if we mill too long, you can see that this peak almost reached like, get into 1, because actually this is the sign of destroying the structure of ordered perovskite becoming a single perovskite. Yeah. So actually there is a limit to what we can do using milling. But how it influences the properties? So you can see here, again, the same praseodymium sample that you can see in here, the initial non-milled sample. First of all, you can see here the, sorry, I lost the pointer. Yeah, I'm sorry, I need to break for a moment, because I guess without the pointer, you've got a little chance of knowing which part I'm talking about. Yeah, I'm sorry, give my computer a moment. Okay, I'm back. So you can see here that non-milled sample, on the top of being kind of slow for the reduction, also exhibit like this inflection, right? So this is this in between half vacancy occupied structure that it's really forming in here is very visible. But milling can actually increase the speed of this process, right? So you can clearly see that we have good results with the increasing of the speed of the reduction in here. So this result was also very recently accepted, and we received a patent for that work. Okay, so now let me go into more practical application. So here I want to compare for you oxygen storage material versus gas cylinder, and compare how it would be if we want to store oxygen in oxygen storage material in comparison to gas cylinder. So in here, in this table, you have few parameters. So for example, the stored oxygen. So I initially decided that, let's say that if I want to store 7 kilograms of oxygen, which is typical value for the gas cylinder. So also for the oxygen storage system, I will also use 7 kilograms. So the volume of those two systems, it's very comparable with the little advantage of oxygen storage system. Unfortunately, here you can see the very big difference in the mass of the system. So the typical cylinder would be way less heavy than oxygen storage material system. And also, if you recalculate it into capacity, again, oxygen storage material, it's not really in favor. Further, there are some special requirements for storing the oxygen using the oxygen storage material. But there are some advantages because, for example, we don't have to stick to the shape of the gas cylinder. We can utilize many shapes, right? But this table actually shows you that for storage of gas, it's a little bit tricky using oxygen storage materials. So where can we use it? And why do we call them still oxygen storage materials? Well, this is a historic name, so that's why we keep it. But let me show you where we can actually practically use it. So here is the figure showing you the exhaust system. And here you can see the catalytic converter. This is an exhaust system for a gasoline fuel car. This is a little bit different. But for the gasoline fuel car, we have this catalytic converter in here. And it plays a very important role to remove the exhausts, because when we are coming from the engine, we still have CO, unburned carbohydrates, and NOxes that needs to be removed from the exhaust gas. So for this, we use the three-way catalyst because there are three main reactions occurring in here. So those are those three reactions that are removing carbohydrates, CO2, and NOxes. But what I can tell you is to remove carbohydrates and CO, we need to burn it into CO2 and water, right? So we need oxygen for those reactions to occur. But for NOxes, we actually need to reduce it, right? So we need reducing atmosphere. So this is the problem because those are two different environments needed. So we can actually solve this problem if we put the oxygen storage material inside, because as you can see here, this is the optimum oxygen content in the environment, so inside of the catalyst here, for all of this reaction to occur the most effectively. So we don't want too much of oxygen there or too little, right? So the oxygen storage material can actually play a role of removing too much oxygen from the reaction or supplying oxygen when we don't have enough. So in other words, it moderates the oxygen amount in the reaction environment. So this is the oxygen storage materials. Actually, ceria zirconia is used for this purpose for almost 30 years already. So now I want to go into the second part of the talk, when I want to present you the temperature swing absorption method, or materials that works with the swing of temperature. So the structure is a little bit different. It's still layered, but in here, the difference between reduced material and oxidized material is in the surrounding of, well, in that case, manganese. So you can see for the reduced manganese, we've got 1, 2, 3, 4, 5 oxygen surrounding the cation. But for more oxidized structure, we have oxygen incorporating the interstitial position. So for the pressure swing, we had vacancy model and vacancies that were available for oxygen. While for this part, we actually need to introduce oxygen into the interstitial positions. But again, the same thing, we preserve the basic framework of the material, right? Because this guarantees the stability of it. So here, I want to first focus on the morphology modification. So I showed you the milling time. So here you've got a milled sample that influenced the reaction versus the material that's non-milled and prepared using standard solid state reaction. But actually here, if we introduce self-combustion method, sometimes called Zogel method, we can increase the specific surface area of the material and reduce the grain size. And in here, in the thermogravimetric results or test, you can see the oxygen content change with the temperature, because a quick reminder, this is temperature swing absorption materials reacting on the change of temperature. So in this test, when we hit the material in oxygen containing atmosphere, it starts to incorporate oxygen and later with higher temperature release it, right? So this oxygen content tells us how much oxygen this material can actually store, yeah, or how much oxygen it can incorporate. So you can see for standard solid state reaction, we are around here, yeah, so let's say moderate oxygen amount. But if we mill such material, then we can actually introduce more oxygen in the same time. Yeah, that the measurements here have been standardized, so the time is the same. And here, if we introduce self-combustion method for material preparation, you can see we can increase the achieved capacity greatly. So morphology modification also works for this type of materials. Further, now let's focus a little bit on the chemical modification. So here you see the parent material of yttrium manganese oxide already prepared using the Zogel self-combustion method. So you can see we can incorporate around 3.3 oxygen into the structure in this test. And you can see if we introduce 30% of terbium into the material, we can actually obtain a great increase of the capacity. This is actually so far the highest oxidized material, the highest amount of oxygen introduced into this type of structure. So how we can use it? If you can see here, if you zoom into this region between 300 and 350, we can actually swing between those two temperatures. So here you can see the temperature was increased into 350, kept there for a moment, then reduced to 300, and we perform such swings of temperature. And here on the black curve, you can see the reply of the sample or response of the sample with the change of the oxygen content. So first the oxidized material released oxygen, and then when we lowered the temperature, the material increased the oxygen content. And you can see repeating cycles of this oxygen absorption and desorption. So just a quick reminder, this is what is happening in the manganese surrounding. So the interstitial oxygen is being introduced in here. So how can we use it? We can actually use it for oxygen production. Here is the picture actually coming from Tokyo Gas. They use it. This is schematic for pressure swing. So they were changing pressure, but you can do the same for changing temperature. For example, if you have a heater here and you just control the temperature. So one of the container will be in lower temperature, one will be in the higher temperature. And if you swing between those temperatures, you can actually produce oxygen from air. So it got very big potential for application, at least in my opinion. But for that, we actually need to improve those materials, those PSA materials, to operate in air. Because so far, I showed you that those materials can oxidize and reduce in oxygen. Yeah. But what about air? So in my studies, I was trying many different combinations. Yeah. So basically today I want to show you the combination of cerium and terbium materials. Yeah, so here we actually tested the work of this material in air, and they show good reply that actually certainly we can notice the change of the oxygen content depending on change of the temperature. Here is a slide of extended studies where we were trying to find optimum temperatures for the reduction and oxidation process. But let me tell you one more thing about these materials, because they're actually quite phenomenal, because they also react on the pressure swing. So as you can see here, well, the change of oxygen content is not maybe that great, but certainly you can see the change in the oxygen content when we are switching from the air and argon. So actually, this type of materials, they can be controlled both by temperature swing and pressure swing. So in my recent studies, I actually decided to combine those two methods. So bear with me. In this complicated schematic drawing, you can see the temperature was increased. This is for establishing the oxygen content in the material, but nevertheless, it was later reduced to 220, and you can see the material absorb, so oxygen content increase, and then we increase the temperature and the oxygen content decrease. And the same thing for oxidation, we use oxygen or air, depending on the color, the line. And for the reduction, you use also nitrogen. So in here, the oxidation was supported by both lower temperature and use of oxidizing atmosphere. But the reduction was enforced by higher temperature and use of nitrogen. Yeah. So you can see here that we are able to use, this is actually, if I recalculated later, this is a possibility of use of 63% of the total available capacity in the studies. So the cycles were actually even out to 1 hour. Well, this study shows that we can actually combine those two processes, both temperature swing and pressure swing, to actually have the greatest change of the oxygen content, and by that optimize the oxygen production, right? Yeah, so just one thing before I conclude. I want to clarify for you that what we call oxygen storage materials is a little bit misleading because it's not always oxygen storage, but we can utilize this high oxygen mobility in the material for other purposes. So not only oxygen storage or air separation using TSA and PSA method, but those materials can be also utilized for oxyfuel and chemical looping combustions, yeah? For solar water splitting, for example, double perovskite. Anywhere where we need to use high purity oxygen, we can use this oxygen coming from the material, right? Also, especially double perovskite that's been recently used for solid oxide fuel cell technologies. The material that I recently presented, so the yttrium manganese oxide, they can be utilized as oxygen scavengers because they got such a high affinity for oxygen that they can actually absorb it from wherever, you know, for example, if you want to purify your argon gas, you will be able to use those materials to remove the traces of oxygen, even from 5N argon gas. And also for catalytic converter, this is what I already showed you before. So they've got many potential applications, very useful materials, at least in my opinion. I hope I convince you in that too. And with this, I just want to quickly conclude the presentation and tell you that all those materials, they need tailoring for the particle application. So we can do it both by chemical and morphology modification and obtain good results. And also, at the very end, I really strongly believe that the oxygen production using those temperature swing combined with pressure swing method can be really applicable for producing the oxygen. And now, at the very end, I would like to acknowledge financial support from Kakenhi Grant, but also my colleagues and collaborators, some of them students, some of them professors, of course. And the work was done in with the help of many groups from many established universities. So I would like to acknowledge that. And thank you very much for your kind attention. Thank you.
Thank you, Alicia, for a very nice talk. Is any question from the audience?
May I ask some question?
Yes, please. Yes.
Thank you very much for a very interesting talk. Actually, I have two questions. One is the you mentioned that the first one, I think it's a hexagonal one, maybe I don't know. Anyway, a PSA material, perovskite, utilizes, you mentioned that the oxygen vacancies. And the second one, a temperature at the TSA material utilizes actually the interstitial oxygen species. My question is that the latter one, I mean, TSA material actually utilizes the phase transformation or not?
It does.
It does, okay.
Yes, both of the materials actually go through phase transformation. In here, I just briefly, can you see my screen?
Sure.
Okay, so in here I briefly mentioned that here is the, I didn't go into details, yeah, but yeah, you can see in between we have different crystal structures. So
yes.
actually the change occurs with the change of the space group. Yeah, we've got P63CM and we end up with P63MC. And in between we've got those two compounds possible.
Yeah.
Yeah, so this, yeah.
Okay. The second question is that you also mentioned that in the first case, you said that the I suppose oxidation is much faster than the reduction.
Yes.
So it's very interesting. Usually the reduction is much faster. Usually. So the for instance, in the final part, I mean combination of the PS and TSA, reduction is much faster than the oxidation. So why in this case, I mean, in the slide, why the oxidation is much faster? Because the particularly in the case of the oxygen vacancy mechanism, I mean, an intake with oxygen actually causes the decrease in the vacancy. That usually slower, make the diffusion of the oxygen ions via oxygen vacancy slower usually. So why the oxidation is so fast in this case?
I understand your question. It's a very valid question. In that case, the oxidation process for the slide that I'm showing now, for double perovskite. So the oxidation process is exothermal. Yeah. So
yes.
Exothermal? No, sorry, endothermal. No.
Usual oxidation is exothermal.
It should be exothermal. So yeah, sorry. So this is the thing. It is exothermal, and so then it should actually slow down, right? Yeah. Oh, I'm sorry. You actually asked a very good question.
Yeah. Yes, actually, I'm working on oxides, and we have many colleagues working on oxides as well, including the SPS and TS materials in my department. And I have seen many presentations of their students or something. And anyway, usually the reduction is faster than the oxidation. So I'm very curious about this result.
So what I can tell you for the here, can we see it? Yeah, so in the case of TSA material, you're right, the oxidation is slower than the reduction, but this is the effect of temperature. So because oxidation occurs in lower temperature, so that's why the kinetics is slower. And the reduction is in higher temperature, so that therefore it's faster.
In this case,
yes,
I see.
But for double perovskite, you are right. But actually, it is very exothermal, because I can tell you that sometimes if you actually observe it, piece of material that it's being oxidized, it flames even.
Really?
So it's highly so it's highly exothermic.
So you mean in this case, oxidation can cause the very local heating with the materials. And actually, it's not the isothermal, but actually some partial heating occurs, and it can accelerate the oxidation.
Probably. And also, this is the thing, what you mentioned, the diffusion in the material. So throughout my work, I was trying to get the smaller grains possible, right? But I think maybe the diffusion is not the limiting factor. Maybe this is like surface reaction or something.
Yes.
But
it can be.
Yeah, but as I'm rather bark scientist, this is something that I still need to study. But yeah, thank you for the very interesting pointing out.
So maybe if you change the specific surface area very drastically, maybe you can change, or you can, how to say, clarify what
throughout,
is
but throughout all of the work, even if I use like solid state reaction and Zolger reaction, which gives me the difference in a specific area of at least one order of magnitude. So I still have this proportion. Still, oxidation is much faster than the reduction process. It's always seconds for oxidation and minutes for reduction. So actually, increase in temperature. So here is for 500 Celsius, but of course I've done also research on other temperatures. So increasing temperature causes increase of, speed of the reduction. So improvement of reduction, but the oxidation actually is still within the seconds. So we don't see worsening there.
I think you have to think about is a structure change, right? When you the oxidized case and then reduction case and different direction of the structure change, right?
Yeah, so there is a structure change here between reduced and oxidized material, where oxidized one is usually P1, P-1, and here is P4 NMM usually. but we also have this intermediate kind of stable compound in the middle. So this is what I showed you in here, that for the reduction, this compound, the half occupied, seems to be very stable. But you know, when we are oxidizing material during the absorption, it also goes through the same structure change, right?
Yep.
So I didn't show the in situ studies here, but we did the in situ studies, and they beautifully show the transformation. So nevertheless, whichever way we go through the same structural change. But yeah, the difference in speed is, at the moment I cannot answer this question, so I will for sure take a look at that.
Okay.
Okay, thank you very much.
Yeah, thank you.
Okay, thank you again for a nice talk. And I'm so sorry I had to close this session. So let me introduce Dr. Shrikant Saini from Kyushu Institute of Technology, and he will talk about thermoelectrics. Okay, thank you.
So can you hear me clear here?
Yes.
All right. So I shared the screen already.
Yeah.
The screen. Okay.
Thank you.
Okay. Thank you. Thank you for organizing such wonderful event. And sorry that first talk some technical problem came up. I hope he will fix it soon. So this is Shrikant Saini. I work in Kyushu Institute of Technology as a researcher. Okay, let me pull out the laser. Yes. So first of all, thank you to the organizer and Professor Mele for organizing such a nice event. So today I will be talking about tuning of thermoelectric parameters for sustainable energy development. This tuning is to help or enhance the performance of the thermoelectric material. So this will start with the introduction, thermoelectric effect, and the key parameter and approaches what we are going to use to enhance this performance, and some example of the different materials, and a final I will give some summary. So let's start with the introduction. So this is the graph which shows the annual increase of the primary energy consumption, which is around 2.66% average. And on the other hand, the decay in the extraction of the fossil fuels. So that means there is a possibility the other kind of energy sources helping to enhance this performance or replacing to get in the energy spectra what we are using every day. This is the possibility and people are awareing towards it, but still we have to go a long way to understand it. So this is a very broad understanding of the energy spectra, what is happening. So if we go in a very focus area, suppose our home, which is connected with the many different instruments and the different power cord with the sensors. So these connections all done with the different energy sources, but the things we are entering at the moment is the internet of thing, which means you have a freedom to control or to connect all those appliances using a smartphone or the portable device. So to understand this, if you see this graph, how these devices are increasing. So these are already populated more than a couple of times of the human population on the earth, and also the penetration rate of these devices in the market is increasing. That means this has a lot of the scope, as well as there is a lot of work to do on this to make it better, because there are many places which you have a devices, you need an energy source, and those sources are not completely I mean, you have to do the maintenance, or you have to change the battery, or you have to keep an eye like what you are doing on that devices, or sometime those devices need like a work in the dark. Of course, like if those kinds, suppose you have a phone you can put in the pocket, there's no sunlight. So those kind of challenges we have in those kind of devices. So the requirement to develop such kind of energy source, this is the work which we are doing to understand this device should have sustainable performance, and it should be easy to fabricate, and it should be economic. Of course, if it is very expensive, it's difficult to buy for the like for the market, and also it is difficult to replace all those which we are using at the moment, which is a lot of devices, right? So, and it is good to have large area production. So large area production is in the point of view of experimental approach, which means if you can able to I mean, if you can able to produce in a very big area, so in engineering point of view, you can cut it or you can reshape it in a different form, and you can use according to what shape or what devices or what the sensors you are using in particular application. So this gives a lot of freedom and save a lot of time and the money in the different cases. So, but to understand these energy sources, there are already many sustainable energy sources are there, in which one of the name comes with the power source, solar power or the solar cells, which can give a better up performance in this material as well. But the problem is when you use this material in a dark or inside the home, then is the problems appear, or in the night. So that times you cannot do, you have to either store the energy in a battery or you have to move in a different form and store then use it. So in this case, thermoelectric material can help in a much better approach, because for generating thermoelectric material, you need only temperature difference, and there is a no maintenance requirement as the other material or other techniques required. So this is the thermoelectric. I will give very small introduction about thermoelectric, what it is actually. So thermoelectric is a direct conversion of heat difference. Suppose you have a material which you have a temperature difference over here. One end is hot, one is cold. This generates some induced voltage. This effect known as the Seebeck effect, which used for the energy harvesting. On the other way, if you see, you apply a current in the volt or the voltage at a material, and one side become hot and the other become cold. That is a Peltier effect, which used for the cooling. So this is the basic effect what we are studying in this case. So what finally we can make with using this device, like these effects, are the energy harvesting using thermoelectric effect or the Seebeck effect. And on the other side, we can make a cooler as well, which helps in the which uses the Peltier effect. So cooler case, there are many advantages has been used. For example, so today I will be talking mainly about this energy harvesting approach, but the approaches which is controlling the parameter can be used for the Peltier effect as well. So Peltier effect or the cooling is mainly used at the moment, like I guess as I saw 2 3 years before, the Samsung already made a small refrigerator, and they also made the car seat, and they have a car like cup holder which you can keep as a hot and the cold drinks in that. So there are many various application in that point of view. And even the micro label, when you have a microprocessor and you want to cool it down, or the you need a point cooling, so Peltier if cooling works much better in that case. So because it has a very fine precision in the current you can see, and the temperature you can change much better. But today I will be mainly talking about the energy harvesting. So these are couple of examples where we can use this application. So as I told, this doesn't need any maintenance, or it once you fix it, its lifetime is longer and it goes much better. So it's very good application for the far remote space approach. And also it can be used for the daily life, for the energy conversion, for the stick with the body, or just like in your maybe in your car seat, even you're sitting. And you can use in the car exhaust, which is has a lot of heat waste over there. So that also you can stick here and you can get energy from there. So there are many different applications are possible in this kind of material. And also recently it can be helped in the health sector as well, where you can have a sensor, or you need an energy source which you can stick with your body and monitor the thing. So that is the some of the things which you can use by using this energy source. So these actually, if you see, I mean, any material which you heat can produce the induced voltage. That means uh, any material can be used here, but the problem is there are parameters which need to fix to get a better performance of this. So we see what are the parameters and how the people are using different approaches to understand those parameters and overcome those issues. So for any thermoelectric material, their efficiency is can estimate using dimensionless figure of merit ZT, which is depend on sigma S and thermal conductivity. This is the formula for that if you are considering at a particular temperature. So if you see this mathematical formula, it is very straightforward. I mean, you can simply use the understanding that if you want a, so the better the ZT, better the performance. So if you want a better ZT, so you can increase the electrical conductivity, you can increase the Seebeck, and you can reduce the thermal conductivity, considering temperature is a constant at a particular time. So if you are using these parameters, so it looks very simple. But when you go in the physics and try to understand what these parameters are, life changes a lot. Suppose you take example of thermal conductivity, which is the electronic part, and the electrical conductivity. So thermal conductivity is directly dependent on the electrical conductivity. That means if you try to increase electrical conductivity, your thermal conductivity will also increase, which you do not want here. Similarly, if you take example of electrical conductivity and Seebeck coefficient, these both depend on carrier concentration, but in a different way. So in a just opposite way. I mean, so if you try to increase electrical conductivity, your carrier concentration goes up, and here your Seebeck goes down, or the vice versa. If you try to increase the Seebeck, your N goes down, and as soon as N goes down, your electrical conductivity start increasing. That means these three parameters are interconnected, and this understanding of this three parameter is challenging. But people have done the research and they found if you go in an optimum zone, there is a possibility you can, I mean, if you go in an optimum zone, you can get a better ZT here, which is around 10 to power 19, in between 10 to power 20, somewhere here you can get. So if you have to tune, so in that case, you need to get a semiconductor, which is have a electrical carrier concentration in between this. So these are the approaches people are using. I mean, to understand the carrier concentration helps to tune the parameter of thermoelectric and get a better thermoelectric performance. So you can use a different performance people have been using. I mean, nano engineering, band engineering, grain boundary scattering, and reducing the degree of freedom, which means going towards the lower dimensions, and the material engineering. You can design a different material, you can work on a different understanding of material, you can change the material, you can dope it, you can do different. So those kind of things you can do to get a better performance. So here is one example. So what was happening since the understanding of Seebeck effect, or understanding of thermoelectric performance. So when we use semiconductor, the ZT reaches around 1, but as soon as we reach in the quantum region or start reducing the dimension of freedom, in that case, your ZT start increasing and reaches until 2.2 approximately as the highest the time, and it is happened very sharp. That means the quantum effect is working very well, and the approaches to understand this is helping a lot to enhance the ZT. That's what we are doing to understand. So this is, we are like different approaches has been followed. So I will be showing you a couple of example what materials we are working and how we are doing. So in the example there are, so at the moment I'm working on the halide perovskite, and I've been working on the oxide material, chalcogenide considering the spin selenide, and organic of P dot and the hybrid of P dot PSS and other chalcogenide or the oxide material. These different material I have been working depending on their temperature of application temperature. So oxides are known for their high temperature stability, so they are good for the high temperature application, and chalcogenide for the middle temperature range. So that's what here we are using for this particular temperature range. And also the hybrid and the perovskite, those are known very well for the room temperature application. So we are preparing those for the room temperature application devices. So different devices we have made and different material we have used for understanding this spectrum of this material, or understanding the different temperature range of their application. So I will be talking of the two different material here. One is the oxide. So in oxide case, the advantage of oxide is easy to prepare, and it is potentially low cost. So I mean, it's not expensive in that sense, and non-toxic, and stable at high temperature. That is a very important point for using. It gives the application for the high temperature. Now, I give you one example of a P-type material. So that is calcium cobalt oxide is a P-type bulk. We worked on the bulk material of P-type. In this approach, we use the precursor of the different material, and we squeeze it in the uniaxial direction, and then we press in the pellet using isostatic pressure. So isostatic press helps in case of reducing the increasing the packing density. That means there is a less gap in between the grains. So that helps a lot and increase the other property which we have seen in this case. Especially it helps to increase in our case the mobility of the material. Now, if you see the XRD, so we use this material and we did engineering in this material and dope the terbium on the calcium side. And then we found as you dope the calcium for the different doping label, until 0.5 it goes very well. After that, it reaches almost the solubility limit, and then it goes start changing the structure of the material, which is here. I think 0.6 is the solubility limit, then it start changing the structure of the material here. So that's what we see in the XRD after making the palette. And then we see the SEM image, what is happening here. So when we take the pure material, so pure material shows like a flake kind of a structure. So this flake kind of a structure is a grain of flake kind. But when you dope it, you get the interdiffused grain, and the grain size is also increased, and it's become like a chunk, probably you can call, and it's like a 2-3 flakes are connecting together, and it is interdiffused very well and quite of melted in this case in all the scenario if you see this kind of SEM. So here, after that, we perform the XPS to understand what is the oxidation state and how the charge transportation is helping in which way. We try to understand. So here we see when we dope the terbium, the cobalt peak is shifting. There's a very small shift, but there's a small shift, and that is shifting away from cobalt 4 plus state. This is what we found here. This helps further in understanding of the electrical property. And on the other hand, we found terbium exists not only one but many different oxidation state. That also helps to understand how this terbium is incorporating with the calcium, and it is reducing the carrier concentration of the material, particularly for our case. So we performed this experiment and we found ZT, which was reported by in the scientific report before, and we reached ZT around 0.7, approximately 0.7 here, and that was one of the best for using the p-type material with a different heavy ion doping. So in this case, what we understand is isostatic pressure was technically helping us to enhance the packing density of the pellet. That was very good to help understand the mobility of the material is increasing. And also, we understand by the XPS analysis that the terbium doping causes a reduction in relative concentration of cobalt 4 plus ions, which gives rise to the larger S, because the carrier concentration is going down. That means S will increase, which happens in this case. While the terbium is a heavy ion, so that helps in phonon scattering. That means it reduces the thermal conductivity. So at the same time, we attack on the two parameters and we got a better result in a single performance. So this is what we understand in the oxide case. The work was attracted by different media. So this is one of the example of the Wall Street Journal. It was I was working in US at that time. So this was we make a module as well, and the performance was I do not remember exact the number, but performance was very well in this case. It was using only the single p-type leg. We made the module, and so that was about the bulk material. So now in the bulk material, so you can do a different kind of doping, different kind of material incorporation to change the parameter and to tune and reach the nearby higher ZT which you are required there. Now, if you change this form in the thin film, so thin films are helping in many cases. Suppose these are light in weight thin films, and shapeability, it gives you freedom. You can shape in a different curve structure, or you can make a different style or the different structure in the easily the shape and the structure as well. And in thin film case, it is much easier to do the nano engineering at the nano scale level. Means you grow the film and you can put a different particles, or you can use a different approach. You can work on that. So here I showed this example again back, which shows like here when we enter in the quantum region, where the bulk was changed in the thin film form. Since then, the ZT is increasing. That means thin film has a lot of scope in the performance. So what does I mean by using the thin film here? So suppose you have a bulk material which you can transform in the thin film. So here I give a very small, very quick example of the aluminum doped zinc oxide. This is the N type of material. So we had a pellet. We made the thin film of this material, and we got it very promising result where the bulk material is here ZT, and the ZT of the thin film, which enhances almost the 5 times in a only transforming to the thin film approach. So this is one of the result we got at that time. So how we made this film? This film was made with the using pulse laser deposition technique. So in pulse laser deposition condition, you have a freedom to use the different kind of performance which can make a better film. So in this case, what was happening is you have a laser and you get shine the laser and it goes on the target. From the target, you get a plume and deposit on the substrate. So that's what it happens in the making the thin film. And this is in the high vacuum chamber, what we use for making the better films. So as I told, it's easy to do nano engineering on the nano scale. So what does it mean is, suppose you have a target and your target itself has some different material incorporated. So if you put it here, you shine the laser, you get a better thin film, in this case of a different structure, using the, even you can have a nano rod, even can have a nano dots, and you can make a two different material. You can combine these two and get a both combination at the same time. So this helps. So this structure inside helps a lot in tuning the band engineering. I mean, the band structure, you can incorporate two different bands together, and also it works as a phonon scattering center. That means you have a lower thermal conductivity and better Seebeck coefficient. So this is what it's particularly used for the oxide case. So this was about the oxide, which is the high temperature application approach. Now I will be showing you the approach which we use for the thin film and at the room temperature application. Then, so for that purpose, we are using halide perovskite. Halide perovskite is a new material for thermoelectric performance point of view, and especially it is used and sold is one of the best performance in the solar cell application, which is, but in the solar cell application, when it was introduced, it has a lead combination in this, and lead is restricted in many countries, cannot use, so, and it's not good for the environment as well. So that's why people replace that lead with tin, and they make a compound which is the ABX is the general formula of perovskite. So we use CSSNI3, which as lead replaced, tin is replaced by the lead is replaced by the tin, and we make CSNI3 material here. And this CSNI3 shows low thermal conductivity and high Seebeck. Then in further development, suppose this is a material which helps in the phonon scattering center, which is here, it is helping. And so if I replace this with a different material, the people has replaced with this with the organic molecule, with the methyl ammonium, and then we got a much bigger atom here, or much bigger chain here. So this increases, this decreases further the thermal conductivity, and that was one of the best, I mean, reports so far is there, I mean, for the lower thermal conductivity. So in this case, you have a hybrid system which has a part of organic and part of inorganic as well. And so this cation especially is uses for so this shows the rattling motion, which helps in enhancing the phonon scattering, and with the phonon scattering you get a lower thermal conductivity. So that is the core of this work and this material. So we work on particularly these two materials and understand their property in a different ways. But today I will be showing you only the performance of MASNI3, which is known as the MASNI3. We'll conclude here with the summary that we showed the oxide and halide perovskite, oxide material and halide perovskite materials. And heavy ion doping is helping enhancing the scattering and resulting lower thermal conductivity, and presence of ionic state helps in enhancing the electrical conductivity and results better in a figure of merit, also in the case of oxide. And n-type growth is still challenging. We are working on that, so future further improvement is definitely required. So these are the, thanks to the funding agency and the different institute where I worked, or this work has been done. And this is the group where I'm now at the moment in Kyushu Institute of Technology. This is Professor Miyazaki, is the head of the group. And thank you. So I'm happy to answer any question if you have.
Okay, thank you, Shrikant, for a nice talk. So, any questions? Okay, so maybe you can ask one.
Mm-hmm.
So you show about oxides. You talk about nanostructuration.
Yes.
In thin films.
Yes.
So this is how to say, still a idea how to do, or there's some result, real result on production of nano defects.
We did some of the work on this, so I did not show here, but like a multi-layer or some of the result we did, but still there are a lot we can still do using the different nanostructure we can implant in this. So some of the result we already did and got a better result, but I have not put it here actually.
Okay.
I just gave an overview of this.
So this room.
There's still a lot of work can be done.
Lot of work. Okay, and one more is about halides. So how really are stable? How
So
really stable they are? I mean,
in air, so
yes.
there are two materials, CSNI3 and MASNI3. So in air, CSNI3 is stable for 3 minutes and MASNI3 for 1 minute almost. So we do not do any work in the air; it's all in the nitrogen environment.
Okay.
But in the device application in future, it need to be done the capsuling, and that is like industry work. So I think it will be okay.
Okay, I hope so.
Yes.
So any question from the audience?
Hello, sir.
Yes.
My name is Subhash. Sir,
Yes,
in halides, I have a one doubt. Like, so you replaced with the cesium with this methylamine. So the oxidation state, like in cesium, if you see that halide perovskite, cesium is the +1. So in this case, CH3 NH3, the oxidation state is like same.
7+1.
Yeah, 1+1. So the bonding with tin, either CH3 or NH3 in this composition. So generally cesium will bond with tin in first case. In second case, methyl group is there as well as amine group is there.
Yeah.
So the bond between tin in organic compound is with the amine group or methyl group.
I think it's with the methyl group only, CHI3HI. Yes, I think so. I'm not very sure actually. I did not remember that.
Because why I go, generally when I compare with amino acids, generally it is with like it will bond with either acid group or amines group. So like that I thought. So
No,
whether
actually, I did not remember exactly group, but I think it was from the methyl, if I'm not mistaken. I do not remember exactly the right now the how was chemistry for this.
Okay. So
But the
I
main,
thought,
but the main goal for this using this is to enhance the phonon scattering. If you have a bigger molecule here, so that helps in the phonon scattering and reduces.
So instead of methyl amine, we can use like we can increase the size also, ethyl amine also.
Yes. So there are report with the other material. Actually, this we did not replace it. I mean, we are doing this is already replaced by some other group, but there are other group also. We are using some other like a chain and the other material here, but that I cannot tell in detail at the moment.
Okay, sir.
But those are really less stable. This is one of the most stable to make actually.
Okay, sir. So I thought like when instead of these we can replace with amino acids also. Like
yes.
Thank you, sir.
Okay, any other questions? Okay, if not, thank you, Shrikant, again. And so Alok is here, so I introduce him again. So
I stop here. Thank you.
Thank you
again.
so much.
Thank you everyone.
So next speaker is Dr. Alok Jha from Kyushu Institute of Technology. So he will talk about superconductors. So please go ahead.
Thank you, Professor Mele, for inviting and for organizing this wonderful meeting. I'm sorry for the past hiccups, but I hope it goes well this time.
Now it's very good.
Okay.
Yes.
So I hope you all can hear me effectively this time. So yeah, I will start sharing my screen so that you can listen to, you can see actually what I want to talk about.
Okay, it's fine.
Fine. So I will just full screen. Is it clear?
Yes.
Okay. Okay. So I am Alicja Kumar from Kyushu Institute of Technology, and today I'll be talking about the role of artificial pinning centers in controlling the vortex pinning of YBCO superconducting thin film. So briefly, I would introduce the critical current density, that is JC. So when the superconductor is in the critical state, I'm talking about the type 2 superconductor. So it is inside the dome of the three critical parameters. So one is TC, another is HC, and the third important parameter is critical current density, that is JC. So JC is actually, when we start flowing some current across a superconducting specimen, we see there is no voltage. When the applied field is less than critical magnetic field and temperature is less than the critical temperature TC. But still there is a limit of the current which we can flow across the superconductor. If we flow some current larger than the critical value, then we see the appearance of voltage and the superconductor goes into the resistive state. It means it is no longer efficient. So there is energy dissipation. So we want this critical current to be as large as possible, also in applied magnetic field. So when the superconducting sample is in critical state, means it is in the mixed state or vortex state, and we start flowing some current across the superconducting specimen, then due to the Lorentz force, which is actually the vector product of the transport current and the applied magnetic field, there appears a Lorentz force which starts pulling these vortices along its direction. And if the vortices or the so-called flux lines, they move across the superconducting specimen, then there is some appearance of the electric field or voltage, and this will lead to some kind of dissipation. So we want to avoid it. We want these vortices to be located specifically at their positions, do not move, so that we can stop their motion and we can stop dissipation. So YBCO is a very promising superconductor, for its TC is much higher than the liquid nitrogen temperature, and it has a much larger critical current density of the order of megaamp per centimeter square at 77 K and zero field. But another parameter which is of very importance is the irreversibility field. Irreversibility field is similar to the critical magnetic field HC2, but actually if the system is below the irreversibility line in this phase diagram of temperature and magnetic field, then we can have some value of critical current density. If the field or temperature is larger than this irreversibility line, then we cannot have any critical current density and we cannot flow any current. So if we compare the irreversibility lines of various superconductors, we can see that YBCO and Rebco means this Y is replaced by another rare earth like neodymium or gadolinium or samarium. So the irreversibility line of Rebco films, these are widely shifted. These are shifted towards higher magnetic field and temperature range. So the range of application that can be thought of in the much larger magnetic field and temperature window. The problem in superconducting films of YBCO or Rebco is JC is high at zero magnetic field, but once we apply some magnetic field, it decreases rapidly. And the main reason for JC depression is at higher temperatures, there are a lot of fluctuations. And also the flux lines or the vortices, they tend to move due to the Lorentz force. So these vortices need to be pinned by some sort of pinning centers. There are some natural pinning centers which are actually defects in the films which are generated during the growth of the thin film, and which can be like vacancies, oxygen vacancies, or voids, or some kind of dislocations, threading dislocations, or some kind of planar defects like that. But the strength of these naturally grown defects or pinning centers is not so high. So we need to introduce artificial pinning centers. Artificial pinning centers means the pinning centers or the defects which are intentionally introduced into the superconducting matrix. So in this slide, you can see different dimensions of artificial pinning centers. So these are linear defects. These are linear defects growing across the C-axis of the film. And this can be introduced by irradiation of the film by heavy ions. Or there are some materials which, if we incorporate into the superconducting Rebco films, they self-assemble in the form of columnar nanostructures. So they are called one-dimensional artificial pinning centers. And we have some planar defects like twin boundaries, etc. These are two-dimensional artificial pinning centers. And we can control the twin boundaries by various annealing conditions or something like that. And the third kind of artificial pinning centers is the three-dimensional, that is the nanoparticles. So some secondary phase material, if we introduce these into the superconducting matrix, they self-assemble in the form of nanoparticles and not in the form of nanocolumns or columns or so. So depending upon the geometry of these artificial pinning centers, columnar or two-dimensional or spherical, they have their different effect on the critical current properties and its anisotropy. So in this talk, I would talk about like how we can use a surface modified target approach to control the microstructure of the superconducting film and how it can enhance the critical current density and control its anisotropic character. So I will introduce, I will a little bit talk about what is surface modified target approach in pulse laser deposition system, and what is the hybrid artificial pinning center approach. And then I will show some results, and finally I'll conclude my talk. So in this section, I will talk about the three-dimensional artificial pinning centers, that is so-called nanoparticles. So in this part of the work, we have tried to introduce the nanoparticles of 211. This is another YBCO, but it is a different stoichiometry than 123. So Y211 was used long ago when a group from the Air Force Research Lab in USA, they incorporated Y211 secondary phase material into the Y123. And in this scanning image micrograph, you can see the appearance of the particulates, large multiple particulates of Y211. And the TM image shows that they grow like in the form of large particles near the interface of the substrate and film, and then the smaller nanoparticles in the other part of the film. The effect of these 211 nanoparticles were observed in the highly increased critical current density in the applied magnetic field. Remember, this is pristine YBCO, and this is YBCO with Y211, and different concentration of Y211 nanoparticles. So JC is considerably improved in the applied magnetic field. So, but in their study, they did not conduct any anisotropy study, like how these Y211 nanoparticles are effective in reducing the anisotropy of this. So I will show you our experimental setup that we use to make our samples. So this is the typical the schematic diagram of the PLD setup that we have in our laboratory. So this is a rotating target, and we have our substrate here and other usual assembly. What we do in the target is we make it slightly different. So this is pristine YBCO target, and we attach a thin rectangular piece of secondary phase, in this case Y211. So as the target is rotated, these two portions, like YBCO portion and Y211 portion, these are ablated alternatively, which gives rise to the composition of YBCO and Y211 in the final film. And we can control the content or the concentration of Y211 in film by simply changing the size of this Y211. So in this study, we used 3 concentration of Y211, 1.8 area percent, 3.6 area percent, and 5.4 area percent. This is the area percent of this Y211 rectangular piece compared to this whole target area. And these area percents are different concentrations are termed as Y211A, Y211B, and Y211C. So let us see the microstructure. So these are the cross-sectional transmission electron micrographs of Y211A. We can see the formation of some nanoparticles. This is the same sample, but at different magnifications. As we increase the content of Y211, we see the larger number of nanoparticles appearing in the thin films. And at the largest concentration of Y211, we can see large number of nanoparticles in the superconducting film matrix. So as we change the size of the Y211 piece on the surface modified target, we can increase the concentration of Y211 nanoparticles in the nanocomposite film. This is the X-ray diffraction pattern. So this is pristine YBCO and YBCO plus Y211A, YBCO plus Y211B, and maximum concentration. So at large enough concentration, we can see Y211, a peak, a small peak corresponding to Y211, 002, that is, which confirms its oriented growth. Even this is also oriented inside YBCO thin film. At a smaller concentration, we cannot see the peak, but at higher concentration, of course, we can see a small peak corresponding to Y211. This is the irreversibility field as a function of the temperature, and irreversibility field as a function of the reduced temperature, which avoids the effects of TC. So we can see that in the case of the nanocomposite film, the irreversibility line is shifted. This is irreversibility field line is shifted towards higher temperature and field regime. So it shows that the vortex spinning is increased because the line itself is shifted towards higher field and temperature. These are some planar image of the transmission electron microscopy, and we can see the appearance of a large number of twin planes, which are very common in YBCO system. But we can also see the large number of nanoparticles in the nanocomposite film. So we calculated the irreversibility field at 77K, and for pristine YBCO, it is 7.8 Tesla. And for nanocomposite film, it has improved significantly. It's 9.7 Tesla for the moderate concentration of Y211. So how the JC has improved in field JC. So in this picture, we can see the variation of JC as a function of applied magnetic field. And at larger magnetic field, we can see that the JC is considerably enhanced. There is another parameter which is called pinning force density, and which is nothing but the vector product of the JC and applied magnetic field, and this is called pinning force density. When we plot pinning force density as a function of applied magnetic field, we can see very significant enhancement in the value of pinning force density in the nanocomposite film. So these are the results at 77K, and similarly, we also observed a large enhancement in pinning force density at 65K, which is actually a sign that in-field critical current density has improved a lot. So we calculated, we obtained the value of these pinning force density value at 77K and 65K, and we see that in comparison to pristine films, these values have improved manyfold, more than threefold actually. It means that the Y211 nanoparticles are very effective in enhancing the in-field critical current density. These are the angular variation of critical current density as a function of at a different magnetic field. So this is at 77K 1 Tesla and 77K 3 Tesla, and JC as a function of theta. So for 0 degree, it means the field is along the C direction, and the 90 degree means the field is along the AB plane, so along the surface of the film, and C means along the perpendicular direction of the film. So naturally, along the AB plane, JC is high, but in other direction, we can see a strong enhancement of JC in all the nanocomposite films. These are the results at 77K, and further we have a very large enhancement in the value of critical current density in the nanocomposite films at 1 Tesla, 3 Tesla, and 5 Tesla. So the angular variation, it shows that the JC value is uniform for a wide range of magnetic field orientation. And we try to understand how this is possible. Like, this is a huge enhancement, and also this is nearly constant, barring a small region near AB plane. So we try to understand why there is a dip near the AB plane. So we try to understand according to the size of the artificial pinning centers. So this is the typical vortex cross-section along the C-axis when the field is along the C-axis. When the field is rotated from the C-axis, the vortex cross-section changes. So from circulars, it becomes elliptical. And if the pinning centers, these blue net kind of circular structure is secondary phase inclusion, or the pinning centers. If this is large enough, then the orientation of the magnetic field changes the interaction volume of the pinning center with the vortex. However, if the pinning center is very, very small, even if the field orientation changes, it does not make any difference. But if the artificial pinning center is of considerably larger size, then of course the interaction volume changes. So when there are a large number of nanoparticles in the superconducting film matrix, then we try to analyze the pinning potential, and we find that we have a peak at the along the AB plane. And when there are some planar defects which are aligned along the AB plane, like some stacking faults or something, then we have calculated the pinning potential also due to these kinds of planar defects along the AB plane. So we have the variation of the pinning potential like this. So in our system, we have both planar defects like stacking faults or so, and we also have Y211 nanoparticles. So actually these two pinning centers are combined. So we see some kind of crossover near the AB plane. So then we try to understand how these critical current value changes from C-axis to AB plane. So when the field is along the C-axis, the interaction volume of the vortex and the nanoparticle is larger, so we have large critical current density. But once the inclination changes, then we have interaction volume reduced and further reduced, and finally the vortex shifts from the nanoparticles to the planar defects. Planar defects can pin the vortices for a very narrow angular range, but for large orientation, they cannot hold the vortex lines anymore. So we have the appearance of critical current density like this. So this was about only nanoparticle introduction into the thin film. So in this part, I will talk about the introduction of hybrid artificial pinning centers, means 1D plus 3D. So if you remember, 1D was some kind of columnar structure along the C-axis, and 3D APCs are the nanoparticles. So what we do? So in this case, we have slightly changed our experimental plan. And in the last case, you saw that we had pristine YBCO target and we had Y211 rectangular pieces on the surface of the target. So what we did in this time is we made some mixed target of YBCO plus BSO. BSO is barium tin oxide. And barium tin oxide, when incorporated into the YBCO matrix, these grow in the form of nanocolumns. And we already know that Y211 grows in the form of nanoparticles. So we have mixed target plus surface modified target approach combined. So YBCO plus BSO mixed target and 211 surface modified piece. And let us see the result. So these are only nanoparticle introduced sample, YBCO plus Y211. And in this case, we have introduced BSO also. So barium tin oxide, they grow in the form of nanocolumns along the C-axis. So we have both nanocolumns as well as nanoparticles. So we call it hybrid APC, 1D plus 3D. So this is the target composition and Y211 composition in these films. So in both the cases, the formation of the nanoparticles can be observed, and the nanocolumns are observed in the hybrid APC sample. So how do these affect the in-field critical current density? We see in this result. So the red symbol, this corresponds to the BSO, YBCO plus BSO sample, means only nanocolumn sample. And this one corresponds to the only nanoparticle sample. But when we combine both the nanoparticle and the nanocolumn, we see huge enhancement in the value of JC in the applied magnetic field, which is also reflected at large pinning force density value of the hybrid APC sample. These results are at 77K, and we also see large enhancement at 65K. So the in-field critical current density of the hybrid APC sample is very, very enhanced, and the pinning force density value is also significantly large. How about the angular anisotropy of the critical current density? So these results suggest that when we incorporate only nano column, we see a JC peak. But when we incorporate both nano column and nanoparticle, we see enhancement not only along the C-axis, but also in the intermediate field regime. This is at 77K 1 Tesla, and this is at 65K 3 Tesla. So the hybrid APC sample, it contains both kinds of features, like a peak, JC peak towards when the field is along the C-axis, and also enhancement along the other angular directions. So in the hybrid APC sample, the suppression of JC along the wave plane is also, it suggests that Y211 nanoparticles may not be uniformly distributed. And also, the geometry and orientation of the nanoparticles within the YBCO, it depends on many factors, including the growth rate. So we tried to explain our results using this kind of modeling suggested in this paper. So when there is a column and field is oriented from the C-axis, there is some portion of the vortex which is held by this column. And more the orientation, the nano column cannot hold the vortex anymore, and it will be free to move. However, in the case of nanoparticles, even if the field orientation changes, there are many nanoparticles which can provide pinning to these oriented vortices. So nanoparticles are more favorable, and if we combine this with the nanorods, this can be very, very effective in enhancing the vortex pinning in superconducting thin films. So following are my conclusions. YBCO films with both 1D and 3D APCs are successfully grown, and the pinning force density values are found to depend systematically on the concentration of the artificial pinning centers, and angular anisotropy can also be controlled depending upon the concentration of both columnar and spherical nano inclusions. So hybrid APCs are very promising for effective vortex pinning. And if we can combine, if we can make a suitable combination of different kinds of APCs, it can be very useful in the controlling the angular anisotropy of JC. So this is all. Thank you for your kind attention.
Thank you for a nice talk. Is any question from the audience? Okay, so may I ask one question?
Please.
So you show surface modified target, and so how is, if you change the speed of rotation, how is affecting field morphology?
Well, yes, it also depends upon the rotation speed. So theoretically speaking, if we have a sectoral piece and not a rectangular piece, if we have a sector piece, it is not, the microstructure is not changing. But if we have this rectangular kind of piece on the surface modified target, then there is a chance of mishitting of the laser pulse near the phase boundary. So we have YBCO and we have secondary phase. So near the phase boundary, there is a chance of hitting. So in our experimental study, we have observed that the microstructure is not the same if we change the rotation speed. So at slow enough rotation speed, we cannot see columnar formation even of the so-called BZO and BSO nanostructures. But for large enough speeds, yeah, we can observe nanocolumns, and we can also control the density of these secondary phase nano inclusions by means of changing the rotation speed of the target.
Okay. Yeah, thank you. So any questions from the audience? No? Okay. So I tried to show my slide, but waiting for this. So I want to thank all the speakers for the very nice talks. And also I want to thank the audience because the discussion was very good. And we were able to find several interesting topics from this workshop. I cannot show you, but I want to say something about how this virus is affecting not only our life, but also academia and research. So it's clear that we have to do many things, not the same as we did before. For example, we have to conduct virtual class, and we must do conferences virtually, like today. And we have problems to go to the laboratory. So how we can do virtual experiments? So in this case, colleagues doing simulations are somehow are not changes the habit, but the guys working in the laboratory should change completely approach to the experiment. And it seems to me also the path for publication paper is changed because it's more difficult to obtain fresh data and which is needed for a paper. So I don't have any number now, but I'm pretty sure amount of review and chapters are increasing now. And also when you have to in the middle of peer review, sometimes you have to redone some experiment for the referee, but maybe now it's more difficult. So a kind of a reply we can give to the referee and maybe become longer. So I don't know if the amount of papers in a long time become more or become less. At least, I mean, in material science. So in other discipline, maybe become in medicine, biology, maybe there are more papers now because they study the virus itself. So I'm not an expert in social science, but I think we are still in the middle of this problem, and probably we can understand the real effect of the virus on academia research after 1 year or more. So for the moment, we are just patiently, we have to wait the end of this story, and hopefully we can travel again and go to the conference, real conference, and share toast, because actually a conference workshop without social gathering is not the same. So this is all from me. I want to thank all of you again, and I hope to see all of you in person very soon. Okay.